It is being organized by the Indian Institute of Technology, Bhilai. So I'm Dr. Mahavir Sharma, the coordinator for the event. Okay, so for the first session today, we are really pleased to have with us Dr. Gautam Samanta from the Physical Research Laboratory in Ahmedabad. So Dr. Gautam Samanta is an associate professor, and he heads the Photonic Science Laboratory at the Physical Research Laboratory in Ahmedabad, India. He did his doctorate from the Institute of Photonic Sciences, just abbreviated also as the ICFO, Spain. And to name a few, his major research interests are in the areas of structured laser beams, nonlinear generation of structured beams, optical parametric oscillators, development of entangled photon sources with high brightness, and apart from the research, he is also an avid educator, where he promotes the optics and photonics among the students of the schools and colleges through hands-on experiments. So we are really pleased to have him with us. So so with this, I would now like to invite Dr. Gautam Samanta to kindly deliver this session. So Dr. Gautam Samanta.
Yes. Yeah. So let me share my screen. Okay. Hello. Good morning, everyone, and thank you, Dr. Sarma, for the kind introduction in the morning. I'm really pleased to give a talk on my research topic, what we have been doing since my joining here in PRL in 2010. So today I'll be talking about the nonlinear interaction of structure beams in classical and quantum optics experiments. So that is some of the experiments we have done so far. I'll be explaining mostly on those. So as already mentioned, my name is Gautam Kumar Samanta. I'm working in the Physical Research Laboratory, Ahmedabad. Okay, so this is the front face of my laboratory. It's a clean room facility because we deal with various laser systems and high power laser systems. So material degradation is one of the factors that limits us. So that's why we have this ideal situation for the laboratory environment through this clean room facility. Okay, and before going or telling about the topic or the research today, so I should acknowledge the support of my group members, those who are present at this moment is all these bright people, and then I am also lucky to have good collaborators from India and different parts of the world. Okay, so these are the expertise research field what we deal with. So we take with a Gaussian beam of various characteristics, starting from the milliwatt power to the 4 millijoule kind of laser pulses we have, and then we manipulate the special structure of the beams. And if you manipulate that special structure, so that adds different new features. So that I'll explain throughout my presentation. And then we also study those structure beams, what we have generated. Now, using this Gaussian beam and then the manipulation of the structure beam, so and adding the nonlinear interaction or parametric processes through different parametric nonlinear processes like spontaneous parametric down conversion, second harmonic generation, some frequency generation, or optical parametric generation. We can generate new wavelengths all the way from mid-infrared to UV. We can generate entangled photon source that is useful for quantum optic experiments or quantum communication. We can generate also new structure beam at new wavelengths, orbital angular momentum, hybrid entanglement, and those things we presently work on with a future interest to go for this quantum communication that even though I have just written in future, but we all are now doing in ISRO and PRL. we are working on towards quantum communication, and then high harmonic generation, and terahertz generation, and null interaction. The topics that's being planned in the near future. Okay. Okay. So we would not be today here talking about the research topic what I am just talking today. Would not be possible perhaps without the support or invention of this man, Theodore Mayman, who invented the first working laser in 1960. So during that time there was a huge competition and for the development of a laser, because a measure was there which is in microwave. Then people are just trying to put this wavelength range in the optical domain to develop lasers. So while everybody was believing in the four laser system, four level laser systems, that is most simplest one, and one can easily get that laser action. But this guy who believed in his thought and used three-level laser system and made this laser work. So that is how it started, the field. And then after this 1960, if you see the timeline of the laser intensities, then you will see that one in almost in first 5 years, there is a huge increase in the laser intensity through the invention of Q-switching and mode locking. And then there is a period, something 10 to 15 years or so, when there was no further possibility of enhancing that laser output or intensity or focused intensity. And then comes something around 1980 to 90, in that range, 85 around, Chuck pulse amplification was invented by Gerard Mourou, who got Nobel Prize in 2018 with Donald Strickland. So then after that, this CPA invention, so the laser intensity has gone up drastically. And nowadays, many countries having that beta watt laser system facilities. People are just looking for the beta watt. So this is the inventions of this slide I got from Professor Mourou's presentation, or also in the net available. So I got that one, but after even though it's up to the 2020, but after that there is some additional enhancement of the laser power and intensity that has gone, but unfortunately the intensity has increased, and then size of the laser system has also changed drastically. This is some part of the laser ignition facility of USA, where Theodore Mayman is holding his first invented laser, and you can see there is a huge change in the size of the laser system. In fact, this laser ignition facility is hosting in 3 football ground area to get that laser for ignition facility. So even though the laser power has increased, or peak power has enhanced from starting 1960, it has enhanced to a different level, and size has also changed. But one thing that has not changed with time is that wavelength coverage of the laser system. So that is very important to know, that it's not possible to get laser wavelength at any wavelength you want. So because you cannot really just find out the laser gain medium, which is having all the features of the lasers, while the wavelength is falling in anywhere you want. So that's why all the lasers market, whatever is available, if you see, the coverage is very discrete, and there is a huge gap also in the electromagnetic spectrum, where you cannot really get any laser system. Whereas those laser wavelengths are also important, because for various applications. So when the laser was being developed, or when it was developed, people used to consider this is a problem-seeking solution. So you have a solution, you don't know what is the problem. But nonlinear optics, nonlinear optics is something that help us to bridge the gap in all these spectral regions where the laser action is not possible. So because those wavelengths are widely used or of paramount interest for various experiments like experimental fields like quantum optics, that is emerging field at this moment, and then imaging biophotonics you name, and then you can find out that when there is a certain need of a particular wavelength for each of these fields. So given this, since it's a laser action is not available in all desired wavelength range, but the application demands such wavelengths, then the birth of a new field came in is the nonlinear optical effect. So this is the effect which can produce. So nonlinear optical effect was it's all the way back in 1875 where Kerr effect was reported, or Pockel's effect was also there in 1895. And in World War II, Professor Brian O'Brien of Rochester University, who developed an icaroscope to see the objects. So basically, this during World War II, enemy or whosoever you think that basically dropping bombs, keeping sun behind. As a result of which, it's very difficult to target that objects, flying objects. So he invented this icaroscope, which helped them to see the objects, even the bright background was there. So in that case, so in all these cases, it's basically nonlinear interaction was there, but nobody really thought that one can change the wavelength of the radiation using nonlinear interaction. So then in 1961, Peter Franken, who first demonstrated, so you see the timeline of this paper is 1961. 1960, the laser was invented. Within 1 year, he demonstrates the generation of optical harmonics. So it's an optical harmonic means we are generating different wavelengths. So he took a laser and focused that laser beam in ruby laser. That is what it was available at that time. Then he used a quartz crystal, focus that laser into the quartz crystal, and then use a prism system to separate that wavelength. So it's a single, it's a fundamental wavelength, and then a second harmonic. And then he submitted the paper. So with the photograph of the spectrum, is this is the input beam, and there is output beam at the second harmonic wavelength is here. But unfortunately, you cannot see that one because the editor of this photoreporter of this journal removed that, thinking that it's a dot, but that is the piece of information which was the cracks of the paper. Anyway, so even though the removal of that spot doesn't really stop anyone, and that is the first demonstration of second harmonic generation or generation of new wavelength. Okay, so now I have talked about some of this generation, and then we don't know really what is nonlinear optical effect. So just to understand that one, I have drawn a pictorial diagram of an atom where the electron is orbiting in a circular path. So if there is no external field, then there is no dipole moment. So net polarization is 0. Now, if you put an electric field through light, then the electric field of the light will push that electron away from the nucleus, forming a dipole. And this dipole will also oscillate in that varying electric field of the light. So that is a dipole oscillation, and that oscillating dipole will emit radiation. So if we then write down the polarization, net dipole moment per unit volume, then we can get that one is proportional to the electric field with the material parameter chi1. So as you can see, the emitted radiation is having the frequency same as the driving frequency. This is a harmonic oscillator region where the wavelength, whatever is incidenting on the atom or dielectric, so that remains unchanged. So that is what we see normal in our daily life. Is linear reflection, refraction, all these are the linear effects where you don't see any change in the wavelength. Now, if we keep on increasing this electric field, then this polarization no longer will be a linear. So you have to add some additional terms. This is a higher order term. So this is the first order term, which is linear effect. Then this is the second order, third order, and fourth order. But today I will be just concentrating on the second order effect or Chi2 processes. So the second order processes, Chi2 processes are some of them are as shown in this slide. So it's a second harmonization where two photons of same wavelength or frequency adds up to generate a new frequency, which is new radiation, which is having energy twice of the incident frequency. Then one can have also two different photons of two different wavelengths or energies, and then they can add. One can have also difference between these two energies and so on. So all these are the second order nonlinear processes. Now, if you have this second order process, and this process is like let's say if you have two different frequencies, so let's say omega-3 and omega-2, and then we can generate a new wavelength or a new frequency, which is the difference of. So in this way, we can just go for lower frequencies or higher wavelength radiation. Alternatively, we can have a strong pump beam and a new input beam, which is very weak, and then we can amplify that. That is basically optical parametric amplification. We can have also one input beam at frequency omega-3, and then we can generate a pair of frequencies, new frequencies that is a signal and idler. This is called optical parametric generation, and this is basically the process what is being used today for the quantum optics experiments. I'll come also in my presentation. And then if we put this process inside a mirror, inside a cavity, we're just putting two mirrors and then making an oscillator. So in that case, it's forming an optical oscillator where we can go for higher output powers. Okay, so by convention, basically, the signal idler is a signal wavelength will be smaller than the idler, or energy will be more than the idler. Signal wavelength is lower than the idler wavelength, or energy will be higher than the idler wavelength. Okay, so all these processes basically governed with this Maxwell's equation, Maxwell's equation, and then if we have three interacting fields, let's say one pump and creating two other frequencies, so then their variation of the electric field over the propagation distance through the nonlinear medium, that can be written using this three-couple amplitude equation. So, and as you can see here, it's a let's say variation of the electric field of wave E1 over the length of the crystal is proportional to the electric field of the pump and the complex conjugate of that other frequency, and e to the power ikx is that term is a phase mismatch. So all these processes, whatever I have said, and then from this nonlinear interaction, we can get two equations. So one is the energy conservation, where the input energy has to be equals to the output energy, because these processes are basically parametric processes and far away from the absorption band of the material. So the parameter of the system remains unchanged despite the nonlinear interaction. And again, since we are just dealing with different wavelengths and a normal dispersion of the medium takes place, so in that case, we will have always a phase mismatch between the interacting waves. But the nonlinear interaction for efficient energy transfer from one field to the another field requires this momentum matching. That means the refractive indices or the K vector of all the interacting waves has to match this equation. So basically, by energy conservation, I mean that 1 omega-3 is equals to omega-1 plus omega-2. And then ideally, you can have this momentum mismatch is 0. That means it's a K3 is equals to K1 plus K2. But in practice, if there is some mismatch, so that can also be handled in the experiment. There are various techniques, because since different wavelengths are there, it's impossible really to get any material which is having refractive indices in this way. But we can explore different mechanism in the phase matching that I am not covering today here. But in case you have question, I can always answer. So basically, different schemes are there, like different phase matching techniques are there, through which means basically we are exploring different parameters of the material to get this equation right. Okay, so as I said that one initially, that different types of the structure beams we deal with. So these are the special structure of the beams we are dealing with. It's a vertical vortex. Mostly we deal with, many of us might be aware about the Gaussian beam. or basically various applications require Gaussian beam, because when if you are having a fundamental mode, then and you can focus it to a diffraction limit. So Gaussian beams are widely used, even in case of nonlinear interaction also we use Gaussian beam. But if you modify the spatial structure of the beam in terms of, let's say, vortex, hollow Gaussian beam, airy beam, perfect vortex, Bessel beam, and vector vortex, these are the beams we deal with in our lab. So I'll be explaining some of this in today's talk. So when you are modifying this spatial structure, then on top of this laser radiation playing a role, it also adds additional features to the process. So that I'll be explaining. So these structure beams have a variety of applications. So starting from this optical trapping and tweezing, then manufacturing also, because you can just focus the beam with a different size and different spatial structure. That adds to the manufacturing of materials, and then optical communication. So addition of this optical vortex or orbital angular momentum adds to the enhanced bandwidth and security. Light sheet microscopy using airy beam also, that helps for the tomography, because nowadays this airy beam and Bessel beam are used. And super resolution microscopy also is a donut shaped beam. That is Stephen Hale, who got Nobel Prize for this high resolution state microscopy. So he used that this donut shaped beam for super resolution microscopy. These are some of the applications, but there are a variety of applications that I have not covered. Okay, now the question comes immediately: how we generate those beams? So let's say if we take a Gaussian beam and then take some mode converter, which will convert the spatial structure of the beam. So the mode converters basically exploits the amplitude and or of the phase, where a transmission filter, metasurfaces, diffracting optical elements, spiral phase plates, and many things are there. Many mode converters are available. Let's just explore in different ways that can generate all these desired structure. So if you want this structure beam, so then you modify the mode converter accordingly, or select a mode converter accordingly that can transform this kind of beam. So one of the example I can see that for the generation of vortex, let's say we take a Gaussian beam and then we make a holographic grating. This is a fork grating, and then if we diffract that beam in that first order, you will see donut shaped beam. To know whether that's the beam, so you do this interference of the Gaussian beam with the vortex beam, then we will see the fork pattern coming back, or the spiral pattern, depending upon the wavefront of this. There is another simplest technique of identifying whether that beam carries orbital angular momentum or not, or vortex modes or not. So we can use a tilted lens. So you can just have a lens and then tilt over its axis, and then in the focal plane we can see it's a splitting of the modes are happening. So depending upon the optical vortex order, so it's a number of lobes will increase. So if it is a L, it will be L plus 1. So holographic techniques basically deals with this nowadays is a special light modulators are there, but those are very low damage threshold devices, which is having very low damage threshold. So for other applications where you need a high power vortex beam, so in that case we use spiral phase plate, which is having a staircase thickness variation in the transverse plane. So if you have a plate and that in the transverse plane, the thickness variation is there, and this thickness variation gives the phase variation in the beam, and we can see the donut shape. And using these, one can have different orders of this spiral phase plates. So 2, 3, 4, and so on. Nowadays, it's 8 is also available. Now, what is optical vortex? So optical vortex beams, unlike this normal Gaussian beam, it is having donut shape, donut special. It is a intensity pattern is donut, and the phase profile. So if you are just studying its phase profile, it is having a helical phase wavefront. So the phase front will be varying in a helix. So if you are taking a snapshot of this phase profile in a particular plane, we will see that there is a phase variation in the transverse plane from 0 to 5. And that intensity distribution, if we are taking that intensity distribution, it looks like a donut kind of shape. And this phase variation can go up of multiple of 2 pi. So if it is 0 to 2 pi, then the order of that vortex or the topological charge of the vortex is 1. Now, if it is 4 pi, then it's 2, 6 pi, it's 3, and so on. And interestingly, even though this optical vortex was invented or demonstrated, but the realization of optical vortex is carrying orbital angular momentum per photon was lately understood, and that this discovery helped a variety of application of this kind of these beams in quantum optics experiment. So optical vortex beam carries an orbital angular momentum of mh cross, where m is the order of the vortex. So if it is order 3, then 3 h cross per photon. Okay, so and then when we are taking these vortex beams, basically the electric field of the vortex beam, unlike the Gaussian beam, so Gaussian beam is this part is there, and additional part is coming here for the vortex. And what you can see in there's a order dependent to the R, means in the special extent. So if it is 1, then the intensity distribution looks like this. So if it is 2, 3, 4. So as you can see, the size of the beam increasing with the order. So if you have higher order, so the size of this donut will keep on increasing. Okay, so this is one of the demonstration we have in the lab. So we have a lens, and then we are seeing the total reflection of the vortex beam. So you can see this part, it looks like it's a cylinder kind of thing. So the vortex is like this, and then it's propagating in this kind of cylindrical form, and then you see that the vortex shape remains unchanged, and then due to this propagation, the divergence is there, and you can see that film is diverging. In nature also, this kind of vortices are there, like water whirlpool, or in black hole, or tornado, or a galaxy. You see that one, that vortex nature is there. Okay, so once we know that one is in optics also, one can generate such kind of optical vortices. Then we try to study in nonlinear interaction whether the nonlinear interaction adds anything to it or not. So in case of nonlinear interaction, so far I have explained that there are two conservation laws. One is energy conservation, another one is momentum conservation. Then we try to see whether there is these two conservations are satisfied, or it's adding anything else to it. So to study that, so we use a laser. This is a black box femtosecond laser. So we attenuate that laser beam, and using these spiral phase plates of different combinations and putting it different places, we can generate this optical vortex beam of different orders. So it can go to order 6, and then took that beam using a wavelet to rotate the polarization state, and then focused at the center of the nonlinear crystal. It's a BIBO, Bismuth boron crystal. And then what we have done, we have just separated this generated radiation and fundamental. So because we are studying that second harmonic emission, we expect that wavelength to be half. And then we study the special structure of those beams. So here is that intensity profile of the palm beam at 1064. So for order 1, 3, and 6, you can see that one intensity distribution shows increase in that donut in profile or radius. And to confirm whether there is because you can have this donut in beam profile without phase variation, that I'll come later. But then if it is a vortex, then that should also have this phase variation. That's why one need to see the phase pattern. One need to use this interference. So we use this beam and then interfere with the Gaussian counterpart. And then we see that one there is a fork pattern 1, and the number of fork pattern is increasing. So for 3 and 6, you can see here. But as you can see, when it's increasing, it's very difficult to identify what is the number of occurrence. Okay. So then we again measure the intensity profile of the green and use the tilted lens technique what I explained. So we have passed this lens through a lens, and then tilted it over its axis, across its axis, and then you can see that one characteristics lobes are coming. So basically, what is happening? This number of lobes minus 1 will give me the order. So when we are seeing 3, basically it's a 3 minus 1 is the order 2. For 6, we will see that 7 lobes, and 12, we will see that 13 lobes. So from here, when we started with 6, we are getting order in SHG 2, because 2 photons means each of these photons carrying orbital angular momentum of 6h, and that's 2 photons are adding in nonlinear interaction, so that's why it will be 12. So that is what we found, that there is an OM conservation satisfied in such a nonlinear interaction on top of the energy conservation and momentum conservation. This momentum conservation adds to the intensity. So let's say we can just generate higher power if we are having a momentum conservation. Energy conservation is automatically satisfied because it's a parametric process, and then we confirm that one, that momentum conservation, orbital angular momentum conservation is also holding in this kind of process. Now, what we did, we tried to measure the conversion efficiency for all orders. So for Gaussian beam, as we say that one, this nonlinear interaction is nonlinear interactions are intensity dependent processes. So if you have a higher intensity which can be achieved using Gaussian beam, then we can get a higher conversion efficiency around 30%. But when we are using a vortex beam, and that vortex beam divergence is more than the Gaussian beam, so it cannot be focused. And besides that, also it's a central region is a dark region, so where there is no intensity. That's why the intensity of the beams when it's focused is decreasing with the increase of the vortex order, because the area is also increasing. In that case, we see that the conversion efficiency is decreasing. So for order vortex order, it's decreasing. And if you measure the area of this donut, then we see that when there is a linear increase of the order area with the order. So in this process, there are 2 things happening. One is orbital angular momentum is increasing, and second thing is area is increasing. So we don't know whether area is influencing the conversion efficiency or the orbital angular momentum. So for that, since these 2 parameters are independent, so independently controlled, so they are dependent, they cannot be distinguished separately. So it's impossible to really just see whether the orbital angular momentum is playing any role in the decrease of the conversion efficiency. For that, we generate a new kind of beam that is called a perfect vortex beam, where the electric field of the normal vortex is look like this one, and this is the term which produces this donut shape with order dependent. But we can generate, we can remove this special dependence using different techniques are there. So we use also one of the techniques, say formation of vessel beam and then Fourier transform it to generate a perfect vortex, where this radial term will not present. So this is the mathematical expression for the electric field of perfect vortex, where you don't see such term. So that's why in this case, the size of the vortex remains unchanged, even though the order is increasing. So, so that means the order and donut size that are now independent to each other. So in this case, if we can just use this process and then study, then we can find out whether the nonlinear interaction or conversion efficiency is influenced by the orbital angular momentum one. So this is the typical experimental setup where you take the laser beam, and again we generate that vortex beam using, this is basically a Doppler setup. So we take these and then using different combination of this spiral phase plates to convert that beam into vortex. That that vortex beam is passing through a axicon, which is forming a vessel beam, and that vessel beam again Fourier transform to get a vortex beam, and then we use 2 different lenses to demagnify the beam radius or size into the nonlinear distance. And after that, we are just separating this like the previous case. So we are separating these beams and then studying their special structure at different points. Okay. So then if you do it, so in case of linear vortex, normal vortex beam, we can see that intensity variation looks like this. But in case of perfect vortex, the size, this is the perfect vortex, and you can see the size is almost the same for all orders. and that lobe structure gives the order of the perfect vortex. You can see that order is 6, 3, and 2. And in case of SHG, the size looks like this. It's almost the same independent of that. And then you can see also the increase in the number of lobes giving rise to the increase of the order of the vortex, or doubling of the optical vortex of order 6 is doubled into the nonlinear process. Then we study their size, even though that image looks like there is slight variation, but we measure their sizes for the second harmonic vortex and palm vortex, perfect vortex of different orders, and then you can see that flat line, almost the size remains unchanged, even though the order of the vortex is improved. And in this case, when we are just measuring the conversion efficiency, we see that one, so there is the conversion efficiency is unchanged. That means the size in the previous experiment, what we are saying that the size of the vortex, increase of size of the vortex is making the process inefficient, because that power density is decreasing and then only interaction is decreasing. That is confirmed. So, and then orbital angular momentum doesn't play any role. So this is also another example of this conclusion. This supporting the conclusion is that for different orders of this pump vortex, and then you can see the conversion efficiency with the pump power remains unchanged. So, or SHG power remains unchanged with the pump power. So that is adding to the conclusion that the input or vortex order doesn't, or orbital element of the beam doesn't play any role in the conversion efficiency of the nonlinear interaction. Okay, so we have talked about this process. Let's say 2 photons of same orbital angular momentum, and then we are adding that to get a higher orbital angular momentum. Or if you keep on increasing the process, let's say 8th harmonic, then you can just add 8 photons to generate the new radiation with 8 times of the input OM or orbital angular momentum. So in that way we can add. So now we are checking whether addition, so subtraction is also possible or not. So in the nonlinear interaction, so if you have 2 photons of a different OM, and then the resultant OM can be the difference between the 2. So that is what we study here. So what we did, we use some frequency generation. So second harmonic generation is the special case of sub-frequency generation, where 2 input frequencies add up to give a new frequency. So what we have done, we have used a pump intensity at 1064, and then the second harmonic intensity at 532, and then use the second order nonlinear material to generate some frequency generation in the blue. So or UV range, so 355 is the wavelength range. And what we did, we used that vortex order of 1 here, and then for the other beam, the order is -1. So it's a +1 and -1, result has to be 0. So that is what we have done, and then we found there is a donut shape beam, but there is no phase distribution. So that means it's a vortex order is not there, so vortex order is 0. Basically, this can be understood something like this one. So if you have a right-handed screw hole of right-handed thread, now if you just try to push a left-handed screw in that hole, so you will be polishing off all the threads. So that is what it is happening. So in case of one vortex is rotating in a clockwise direction, another one is anti-clockwise direction, so that is they are cancelling their phases, and then the resultant phase will be constant phase or a plane waveform. So that is what it is happening. So basically, we have taken this. This is the nonlinear interaction of this process. So we take that same pump laser, convert that second harmonic, and then the remaining pump we are just converting into vortex, and that second harmonic we are converting into vortex, and they are just passing through the linear crystal and generating this process. So you can see that the hollow Gaussian kind of intensity pattern is coming here. This is the intensity pattern. So it's just a donut shape is there, but there is no phase variation. And theoretically also you can just predict that is what it's look like. Now here all the means so far we have talked about the nonlinear interaction where 2 photons of the same frequency or different frequencies they are interacting in the process and then generating a new frequency. Now we go in the other way. Let's say instead of addition, it's just a reverse process of the second harmonic. Let's say two photons are adding and generating a new photon. We can go back and we start with a one photon and generate two new photons. So that also possible. That is what is called parametric down conversion. Previous case it was parametric up conversion. It's just a down conversion. Now, let's say this is the cartoon where it shows let's say a palm photon goes to the nonlinear interact crystal. So it after this dipole oscillation, and it produces a new photon, two photons, whose energy is conserved. So the pump energy has to be equal to the sum of the energies of the generated photon. One is called signal, and another is called idler. So, and then we maintain that momentum conservation, and they maintain also this orbital angular momentum. So this is something. Let's say the input orbital angular momentum is equals to the orbital angular momentum of the output photons. Now, if you take a case, let's say orbital angular momentum is not divisible. So what will be the process? In case, let's say we have palm photon of orbital angular momentum 1. So since one cannot be divided, so that means it can either go to the signal, and idler contains the Gaussian beam. Because if you have a Gaussian beam, then the OM content is 0. Or the idler can have the vortex mode, and signal can have 0. So which of these two processes? Because if you can just go from this conservation law, so 1 is equals to 1 plus 0 or 0 plus 1. So which of the processes is possible in this case, and why it's so? To check this one, we have basically done some experiment. Like we have a laser, and then converted that into vortex structure, which is having orbital angular momentum of 1. And then we pass to the nonlinear crystal, do the optical parametric generation. In case of SPDC, optical parametric generation is having a certain threshold. After that, the radiation is a coherent radiation coming out, and it's basically, it's as good as a laser. So it's an above threshold kind of process is called optical parametric generation. So what do? We just focus that beam, and then it produces a signal and idler, very simple. And then we extract those beams and then study their intensity profile. So in case of pump, when we are just taking order 1, which is also evident from the splitting of these lobes, then you can see the signal is having the vortex, and idler is a Gaussian beam. So that is what also evident from there, from the lobe structure. And if you have -1, in that case also you can see that lobe structure is rotating because the phase variation has rotated, but the idler is always a Gaussian. Even though we have said that one is say idler can also get the orbital angular momentum. So that is very interesting to see. So in all the cases, the orbital angular momentum is transferred into the signal, not into the idler. So that's we realize that one, because this idler wavelength is in the mid infrared as compared to the near infrared signal wavelength, and that due to this the divergence of the idler is more than the signal. So this mismatch in the divergence is adding additional loss to the process. That's why the most easiest transfer is to the signal. That is what we realize, and then that's it's understood that signal will get, not the idler. Now we try to find out whether is it possible any mechanism where we can selectively switch the orbital angular momentum mode of the pump either to the signal or to the idler. So here basically we have then gone, instead of this single pass optical parametric generation, we tried that in an optical parametric oscillator. So here is an experimental configuration. So again, we take a CW laser and frequency W into the green, and that green is converted into vortex mode. And then this is the OPO in the X cavity configuration. The nonlinear crystal is there. The pump is focusing, and then it's creating signal and idler. And idler and it's a degenerate process where both signal and idler are resonating inside the cavity, and their wavelengths are close by to the twice of the pump wavelength, around 1060. And then what we have done, we have separated the signal wavelength and the idler wavelength in two different arms. one, this arm is the signal arm, and that is the idler arm, and then that cavity is formed. And in case of signal, we just put some output coupler. So when we are just having this configuration, and in that case, we see that for the pump voltage order 0, signal and idler is having 0. That is what is typically we see, and none of them are having any phase singularity. However, when the pump vortex is order 1, then we see the signal is carrying that orbital angular momentum, not the idler. Whereas in the previous case, we saw that one exactly the same thing is happening in this process. Okay, so then we calculated its a threshold condition. It's using dynamic couple amplitude equation. We calculate the threshold condition for two cases. One is the pump OM is transferred to the signal and idler is having a Gaussian. In that case, we get a threshold condition in this form. And in the second case, pump is transferred to the idler, signal is having Gaussian, and then we get the threshold condition like this. So if you see, compare these two, all the terms are same except this gamma S and gamma I, and gamma S, gamma I are these two terms are basically loss parameter for the signal and loss parameter for idler. So in this case, when from this equation we conclude that when loss for the signal is more than the idler, then pump will be transferred to the idler, and if the loss is lower than the idler, signal loss is lower than the idler, then the pump will be transferred to the signal. Means basically, whichever having lower loss, that beam will carry the pump OM mode. Then we did that experimentally again. So in the case, let's say when we measure the transmission curve for the signal and idler, and then we found that this one is the loss for the idler, and this curve is for the signal, and there is a huge variation. So in this case, you can see always the signal loss is lower than the idler loss. That's why we are seeing that OM is transferred to the signal or across the tuning range, and idler is having the Gaussian beam across the tuning range. So even though you have pump beam of order 1, signal is always getting that OM mode of the pump, not the idler. Then what we did, we added additional loss of the output coupler to the signal. So in that case, the idler loss remains unchanged, whereas signal loss is increased. So in that case, we see now the signal is not carrying the OM mode anymore, whereas the idler is basically taking that OM mode of the pump. So you can see here, initially it was a signal was carrying OM. Now it's a signal is carrying Gaussian mode, idler is carrying. So you can see from a fixed input OM mode, we can switch to any of these beams depending upon the loss. So if you can just modulate the loss selectively, you can have a switching of OM modes in from the cavity. So one is there. So we try to see whether when it's a orbital angular momentum of 2 for the pump. So when you take the 2, then 2 can be 2002 and 11. There are 3 possible combinations are there. In that case, we see that when the signal loss and idler loss is very comparable. In that case, we see that both of them are carrying orbital angular momentum. It's just 1-1 division is happening. And when the signal loss is much lower than the idler loss, then we can see that signal is carrying that order 2. That is from that fringe pattern is evident, whereas idler is there. So other condition, we couldn't really just with the existing facility, we couldn't really explore the other possibility. But that possibility is there since these two are happening and previous experiment. So this is possible. So from this study, we can just tabulate all the results in this form. Basically, we have a control parameter that is basically the loss parameter in the cavity, which we can dynamically change for first switching, or we can. But what we have done is basically just changing the meters. So we have a control. Then we have input pump mode, and that can be switched to the signal. And in that case, we can get that output state, OM state, something like this. And for the idler, we can get this kind of state. But if you have higher order mode, so let's basically, just from for higher order OM modes, let's say if OM mode is M, then we can produce M plus one number of output states. So the number of states enhancement or selectively we can just do this control of OM mode. Then basically it is for the communication it can be useful. Basically we are having a multiplexing kind of thing. All states are possible in using this classically or in quantum mechanics. Okay, so so far we have talked. Then we explored some of the other things like let's say instead of just restricting ourselves for OM mode in the near infrared range, can you just transfer into the mid infrared? Because mid infrared wavelength range is essential for a variety of applications in spectroscopy, and then if we can just add also OM mode to that, and OM mode is additional energy, so that can be explored. So what do we try? We try to basically transfer that OM mode to the idler. So for that we have designed a cavity, something like that is a signal resonant cavity where signal is resonating inside the cavity and idler is transferred. In that case, we can have basically the transfer of the pump OM mode to the idler, and then you can see the wavelength range. So all the way it can be varied in different region, whereas signal is having an orbital and Gaussian. So basically that is what is why it is happening. So because the cavity having the Gaussian mode is having is most favorable because the loss of the cavity for the fundamental mode is lowest. So it mostly support that Gaussian mode. And in that case, the gain of the system, if we keep on increasing through the pump power, then we can again explore higher order modes in case of the resonant cavity. So here are some of the results. So you can see the tuning across the wavelength range, the amount of power, output power for this mid-infrared range, where substantial power, which is more than 2 watts of output power we can see. And then there is some power scaling of the idler and the pump. And if you are just increasing that pump vortex order, so there is an increase in threshold because the gain is reducing. So due to the reduction of, so if you want to go for further mode, let's say for OM order 1, the threshold is something around 10. It's for 2, it's coming 15. And if you go for 3, that we couldn't really do because so the threshold will go up, and then if your threshold is increasing, then driving the system with higher power unnecessarily brings the damage to the crystal. So that's why we didn't do. We have restricted our study only up to order 2. But this is basically just giving the perspective about the possible transfer of OM mode of the pump to the idler or the mid-infrared wavelength. So to address this problem, instead of just restricting us to the lower order OM modes, we try to transfer that one higher order modes using different new scheme, where the system is devised in a cavity, and we have basically in the OPU, and then there is another crystal which is basically helping us for optical parametric amplification. It is OPA, where the OPO is started with the Gaussian beam, and then here another pump beam is there which is having a special structure, and that is being transferred to the nonlinear crystal, and then the nonlinear interaction, because the signal is in a Gaussian beam and vortex beam addition, because the signal has to be always in the Gaussian, so that's why the transfer has to happen to that, has to go, the OM of the pump should go to the idler. So that is what is happening. And in that case, basically we can just go all the way to 6 order. So it's a higher order OM mode in the mid-infrared is also possible. Here are some of the characteristics in terms of output power and conversion efficiency. So in that way, we can just go. So so far we have talked about that vortex beam, and then that is leading to the perfect vortex or hollow Gaussian beam. But all those beams, whatever we have talked about, is basically the scalar beam, where the polarization of the beam remains unchanged throughout the transverse plane of the beam. So there is always the same polarization everywhere of the beam. Okay, so we can have additionally, so instead of a scalar vortex, there is a vector vortex where the polarization of the beam varies in the transverse plane. So we can have a radial polarization. So if you are just taking a donut shape intensity profile, and then you can see that when the polarization at different points will be different, and that is something interesting. And it can also vary azimuthally. So such kind of beams can be represented with that electric field of EH, horizontal polarization with minus orbital angular momentum, plus EV, vertical polarization with plus OM contour. So in that way, you can just have a vortex beam or a vector vortex beam. But nonlinear interaction, uh, uh, as we say that one momentum conservation, nonlinear interaction is basically is a single polarization effect. So if you select a nonlinear crystal and phase matching, that works for a particular polarization state. So let's say we have designed the nonlinear crystal for vortex order or for polarization vertical. And if you have a horizontal polarization in the pump, that will be unchanged and unaltered. So as a result of which, if we have this kind of beam, if you want to generate this kind of beam, we cannot really just use nonlinear interaction, because nonlinear interaction either will convert a particular polarization and rest of the other polarization states will be unchanged. So then we try to generate such kind of beam, uh, uh, through the from a cavity or from a optical parametric oscillator. So if you are trying to do that, then we have used some interesting architecture, because gain medium always handles with that a particular polarization. That's why we when the beam is passing through the nonlinear crystal, we keep the polarization linear, but we make the modulation of the polarization in this region. So this is a pictorial diagram of a cavity within two mirrors, and then this cavity is divided into two parts. One is A, and another section is B. We call it B. So in this B section, we make the modulation in the polarization, but when it coming to the A portion, so the polarization will be linear. So what do? We have a linear polarization. Let's say we have a pump beam, then it's generating this vortex, and that vortex is converted into left circular and right circular polarization through this water plate and reflection. And then when it is going to the water plate, it will be a vertical polarized, and then vertical polarization pass through this linear crystal, again go through this polarization rotation, and then when it coming back after one round trip, the polarization state of the resonating beams is same. So that is how we get that back. So, but if you see, if you are extracting output from here, then you have right circularly polarized with a vortex order 1, and we can have also other way, it's a left circular polarized or -1. So this combination will give us a vortex, and there is a general. So even though I have written that one for H, there's a special vector vortex beam, but the general expression will be ER, or right-handed polarization and left-handed polarization. So this is the experimental setup what we have explored. We take a ND as nanosecond laser. It's a frequency double into green, and that green is divided into two parts after converted into using a mode converter SPP, and then we split into two parts, and one part goes in this path PB1, and it's resonating in this direction, and another beam is passing through this path and then focus in this direction, and that is also creating. So there, it's basically in just two OPO inside the cavity, or two optical parametric oscillation is happening in the same cavity, and then we have this water wavelets combination here to convert the polarization mode conversion. So in each round trip, the polarization state of the resonating beam comes back to its original state and interact with the pump, and energy transfer is happening. And whereas in the other section, the polarization is converted into a desired polarization state, or R and L. So if you are taking this form intensity and vortex beam, if you see this one, and signal is having, because the resonating beam has to carry that orbital angular momentum, that is what we confirm here. The signal is having orbital angular momentum like this, so that is also confirmed. And idler is a vortex, that is what we want to show. then the output beam if we have, so if you can just rotate the polarization state. So this is the output beam we get from the laser at 976 nanometer, and this kind of vector vortex beam can be represented through different points in the Poincare sphere or Bloch sphere, higher order Poincare sphere. So, and if we make a, because this vector vortex beam is known also as the non-separable beam, because this here wave mode and polarization cannot be separable. So if you are trying to make a polarization projection in a particular basis, like let's say if I'm just trying to see the intensity, let's say trying to see this beam in anti-diagonal, then you see that OM modes are changing. So you can see that. So from H, and then if you are having different polarization states, so the lobe structure is rotating, because due to this projection, that mode, because they are inseparable, so you cannot really separate the OM mode and the polarization state from the beam. So that is what say non-separable. Okay, so this optical vortex, one of the interesting application of this kind of optical vortices are fabrication in material structure. So fabrication of nano needle. So here you can see a single shot nano fabrication, where you can see that one, because the intensity of the vortex beam is having a do not save intensity profile. So if you have a do not save, then in the center there is no intensity as such. So as a result of it, the material remains unchanged. Or formation of a needle is happening, something around in a nanoscale, and then this is a deep will be there. So each of these, let's say, using a single vortex beam, one can generate a needle, but in case one has to generate an array of needles, then this process has to be repeated many times in a raster scan, and that is a time consuming process. So now what we are trying to see, instead of a single vortex, can you just produce an array of vortex? So that is what we have demonstrated here. So use a fiber laser, then mode conversion, and then using all the experimental schemes are the same as previous. So, but what we have done here, we have just added a micro lens array, which is a two-dimensional grating kind of structure, and that grating structure produces a array of vortices. So if you have input beam, whatever input beam we are having, so output beam will have the array of that input beam. So something like this one. So if you have a input beam at 1064 and then micro lens array, and then this is the phase factor of the micro lens array, which is refractive index, and that the refractive index of the material is wavelength dependent. So if you are using different wavelength, the phase will be different, and then the resultant structure will be different. That is what we have shown here. When you are using a 1064 nanometer, you can see that when 4 strong lobes and then small vortices are there, some lower intensity vortices are there. But whereas when you are just using 532 nanometer, then the patterns will be very different than what we have seen previously. So in this way, changing the wavelength or changing the refractive index of the micro lens, we can just make any pattern or pattern of the beam, desired pattern we can produce. So just to give an example, let's say so we wanted to generate 4 as a 9 vortex array kind of thing. So that is what you can see in case of pump. And when we are doing this nonlinear interaction of that, and also you can see that one in second harmony generation. Also, we can see the array of such input vortices. Okay, and then interesting thing of this system is basically having the control over the size of the vortices and their pitch. So we can control the size. So here you can see there is a particular size. Depending upon the application, you can just reduce or increase the size of the vortices using very simply by moving this vortex micro lens array just simply from its focus position. So from the focus position of the lens, we just keep on changing this micro lens array, then the pitch size or the vortex size will change. Okay, so far I have basically talked about all the processes in the classical domain, and then trying to understand its different architecture with the input beam. For the best interest of time, I couldn't really just cover the other beams like the Bessel beam or the ARA beam, but we can always discuss in case you are interested. But now I'm just going into the not in the classical domain, but going to the quantum domain, where we can deal with very little number of photons and then study its quantum properties. So for this, here we have devised a new experimental scheme where we can generate single photons or entangled photons with high brightness, because when we talk about single photon or quantum optics, as you can understand that photon numbers has to be very small. Again, if the photon numbers are very small, then only you can see the quantum effect. But in any practical application, you need the photon numbers to be high, because otherwise you have to wait for a longer period of time for this application to complete. So that means basically it's a demand is there when you are generating an entangled photon source or a single photon source. The brightness has to be as high as possible, but at the same time we have to just see its properties, quantum properties remain intact. So that's why this is one of the example of those kind of experiments where we verify that there is a certain upper limit over which, if you are going keep on increasing the brightness of the source, then the quantumness of the system will go away. And we have basically generated very high brightness entangled photon source. So using a pump beam in a Sagnac loop with a periodically poled crystal in an oven, and then basically it's generating SPDC photon in both ways. So it's going if the pump photon is going in this direction, to anti-clockwise direction, then the photon pair in the red is going in this way and then it's coming out here. Or if it is going in the clockwise direction, it's generated in this way. But again, they are exactly overlapping and then going in this direction. Now the quantumness is coming because here we don't know when the pump photon, which of the pump photon is producing this pair, SPDC photon or pair photon in this process, whether it's a clockwise photon or anti-clockwise photon. So that we don't know, and that we cannot predict. So this ambiguity is giving the quantumness in this case of or entanglement. So then what do we do? So we basically analyze that photon. So if we are getting a photon here, then another photon will come here because they are just diametrically opposite points with the phase matching condition we have control. So, and then we study whether there is a correlation. So from that correlation, we can verify whether they are entangled or not. And to enhance the brightness, basically we have explored this non-collinear type 0 phase matching. That is some of the terms is why commonly known in case in the field of quantum optics or nonlinear optics. So we found that one in case of type 0 process is the highest conversion efficiency process, and the non-collinear is something that enables us to separate the photons, which is co-polarized and same frequency. So that is how we have just demonstrated. So from the collinear, we can go to the non-collinear, and for the degenerate process where the conversion efficiency will be more. So that is what we have shown. So in the pump, the generated photons will be splitted, and then if you keep on changing the phase matching condition, it can go to the collinear process where all the interacting photons are propagated in the same line. So in this way, we have generated a record brightness in this case. It's a 0.41 megahertz per milliwatt per nanometer in this using this kind of experimental scheme with the state fidelity of something 97.5%. Okay, so the vortex was there. Then we try to see that when we have a classical laser system there, we understand how the transfer mechanism is happening or the transfer is happening. Now, if we try to see that one in the single photon level also, whether that those transfers are possible or not. So here is that experimental setup where we have studied the single photons and their OM properties or the special structure. So you took a 405 nanometer laser and then converted its special mode using a special light modulator, and then took the beam. This is a pump beam, is always a classical beam, which is having output power in the range of milliwatt or so, and then focused in a nonlinear crystal. And it's a type 2 process, a periodical pole type 2 crystal, where the generated photons will be in orthogonal polarization states. So we take that polarization, and then the generated photons are splitted. One is going here. It's let's say vertical polarization is going in this direction, and horizontal polarization is coming here. So we have used it's a re-imaging technique. So we image the crystal plane again and again, and because this one is basically the delay line we have added, so through that imaging technique. So each time it's an image and then re-image, two lenses are re-image, making this in 4F configuration and re-imaging. And then we have again reflected back, and then it has gone through the same path using quarter wave plate. The polarization state is rotated into vertical, so it reflects back here. Now we are basically studying with the ICCD, the special structure of the beam with a condition from the partner photon. So one photon has gone here, another photon through this line is coming back and being detected here in the ICCD. Now the question is why I have added so much delay to get this photon detected instead of just putting this ICCD here. Unfortunately, the date time or the trigger time of this kind of ICCD is something around 40 or 50 nanosecond. That means the partner photon which is being detected here, it sends a signal to the ICCD saying that open the aperture or shutter, but this will take some time where the shutter will still be in the closed mode. So that's why we cannot see the photon. So that means if we are just keeping this ICCD here, then its partner will always be missed and it will be seeing something else. So that's why what we have done. So the partner photon is delayed equivalent to the dead time of the ICCD, so that when it's open, it sees its partner exactly. And then we study the special structure or this triggering mode ICCD. So in case of pump of different vortex order, so we have just gone up to the order of 14 because we are just using special light modulators and we have the flexibility of going to higher order modes. And then you can see from the lobe structure that pump vortex is having orders. Then we are heralding this single photon. So for the heralding is basically just the one photon is detected, and then we are trying to see its partner photon because both the photons will be generated simultaneously, and they carry these features, let's say OM conservation, momentum conservation, and orbital angular momentum conservation. And since we are just collecting the one of the photon in a single mode fiber, that means we are just restricting into a Gaussian mode or order 0. Then the idler has to carry, or the partner photon has to carry the orbital angular momentum mode. So that is what we have seen. So when we are just using for pump order 1, then you can see that coincidence image of the partner photon is having order 1, and for 14 you can see that 14 lobes in case of single photon. And these images are recorded for a longer period of time because you have to integrate for a long time to get substantially large number of photons to see this kind of intensity pattern. And all this, basically all these dots here, you see that in one event at a time, and that took a very, very long period of time of the study. Okay, so then what we have done, basically, just this is, we are trying to understand also, there's when you have a single photon and then you try to interfere in an Sarnag interferometer. Let's say here is the one photon is coming here, and then what we are doing, we are just making a Mach Zehnder kind of interferometer here, and then trying to interfere them and see whether that interference is happening, or we are trying to basically, just like in case of vortex, we saw that one in the plane pattern we are trying to see. Is we are having this fork pattern. We should get that fork pattern for the vortex beam. That is what we are just trying to see. And interestingly, a single photon is coming. Either it goes through this path or that path, and at a time, and then we are seeing this intensity pattern. But in principle, we should not basically see the interference, because either the photon will go in this path and get a spot, or this path get a spot. But this, due to this quantum mechanical effect, where the probability amplitude is there, so this interference is happening. Basically, this is the phenomena which started the quantum optics field alive. because of this double slit experiment. Here it's a magenta interferometer because in case of double slit experiment also you see that kind of interference pattern using a single photon. So anyway, so coming back to this current experiment where we are trying to see, so in coincidence imaging we are interference pattern. So the photon coming back and then we are interfering, and then you can see for palm vortex there is a fork pattern and of different orders that is coming. And here basically it's a vortex interference. Basically, same beam is interfered with itself. That's why for order 1 it will be 2 into order lobes. Basically, if it is order 1, then we will have 2 fork patterns. So here one fork pattern here, another fork pattern here. For 3, we can see here 3 fork patterns, 3 fork patterns here. Like that, it will be. For 8, it will be 8, 8, 16, something like that. Because you don't have any Gaussian part present in this case, or neither you can access the Gaussian part of the single photon. So while we confirm that when the transfer is happening, so the tilted lens, we try to also confirm that, so that through this interference, that is something also very interesting to see, the interference of single photons. Now, when you have this kind of single photons, and then you have to really see whether they are truly single photon or the multi-photon events are there. So for that, we have this HOM interferometry, where it's got Hong-Wu-Mendel interferometry. Here, basically, the photons are bosonic in nature. So, and their bunching will be always there. So what is happening? So we have this SBDC process, and then using this PBS, polarizing beam splitter, we have splitted these pair photons, in one in this direction, another one in this direction, and then we interfere them in the beam splitter. And when basically they are indistinguishable in all degree of freedom. All degree of freedom means polarization, time, and special mode and everything. Then the photons either go to one of these ports. So I don't know which port, but always they will end up into a single port. So in that case, if you are just detecting its coincidence, then this coincidence means if this photo detector clicks, then other has to click. So from there, we try to find out the coincidence. So when we study this coincidence, while delaying one of these photon, so while delaying one of the photon with respect to other, so this photon is fixed, let's say another photon, we are delaying it, and then we are measuring the coincidence. When they are distinguishable, then one of the photon will go into one port, another photon will go to the other port, and we will get coincidence. But if we keep on reducing the delay line, so then the coincidence keep on decreasing, and when the delay is almost negligible or zero, then there will be the minimum coincidence, because the bunching is happening and the photons are going into the one port. And then if we keep on increasing again further, then it will be this kind of globe. This is called Hong-Wu-Mendel interferometer. From this interferometry, you can just see if it is a single photon event or multi-photon event. So if you have multi-photons, then this visibility will not go to near to zero. So from here, from using different pump powers, we have just find out that when the lower pump power, the distinguishability or visibility of this one is 90%, whereas if you keep on increasing the pump photon, then the visibility is going down, because when you increase the pump power, then your generation rate will be higher, and that higher generation rate can end up with a large number of photons, and that will give you the lower visibility. So to coming back to the present context, basically what we are using this. So in the previous experiments, whatever we are just seeing, that single photon characteristics, that is also evident from this HOM interferometry, that we are truly dealing with the single photon events and studying its OM characteristics. And here are some of these characteristics. Let's say if you have a vortex beam, in case of classical beam, we see classical vortex beam of different orders having different divergence, and the divergence goes up with the order. And as you can see here for the pump, there for different orders, the divergence is increasing. And that we have basically just measured. And for the photon Single photon vortex also, you can see that similar kind of vortex divergence in case of single photon when we are doing this coincidence imaging, integrating for over a long time, and then we are trying to see its propagation and the divergence with the propagation, that we can see that one it's exactly following that same pattern like the classical beam in case of quantum. So if you have time, another a couple of things we can discuss. Like I said that one particularly the vector vortex beam or the non-separable classical beam is there. In classical optics you can just do, but using this classical pump beam, that is basically demonstrated here. You can just generate a non-separable state in that electric field vector in this form. If it is a Gaussian, it looks like this one. If it is a vortex, then the intensity pattern looks like this with that electric field as I explained. And then if you are projecting at different orders or different modes using vortex order 3, then you can see these lobe structures are there, and the lobe structure will keep on rotating depending in the different points of the Poincare sphere when you are making a projection in a polarization basis. Okay, so that is what you can see when order 1 is there, then the modes are rotating. When you are projecting, that modes are changing because they are non-separable. In case of order 3 also, you can see this kind of thing. Now what we try, let's say, can you just transfer this classical non-separable state or classical beam where a huge number of photons are there, and then we are trying to transfer it to the single photon level, and then see whether we can generate also higher order Poincare beam or hybrid vector vortex beam or hybrid entangled photons or not. So this is basically the direct generation of hybrid entangled two photon states using classical non-separable state. So we have generated classical non-separable state or vector vortex beam, and then use two crystal scheme for spontaneous parametric down conversion is a cone, and then we have selected 2 points diametrically opposite 2 points because the pair photons will be always in diametrically opposite positions. And then what we did, we fixed one of the photons here using a detector in a single photon mode. So basically, this is a single photon detector we coupled to the single mode fiber, so that we are always selecting the Gaussian mode. But in the other one, what we are doing, we are basically scanning, doing the raster scanning to find out how the intensity or single photon distribution is here with the coincidence. So basically, we are getting a click and then measuring its coincidence with this detector while the detector is moved in that XY plane to see that special structure. And then what we are doing, we are basically in the one arm, in the this arm where the fixed arm, where we are basically making different polarization projection and seeing how the pattern in the other port is changing, because due to the entanglement, basically if you make a projection in one photon, its partner photon will change accordingly. So that is what we are trying to do. So here basically we have a diagonal projection in this arm. Let's say here it's a diagonal. We have adjusted this diagonal polarization in this case of this photon, and then doing this raster scanning. For order 1, we see this kind of lobe, and order 3 we can get 6 lobes. Now, if we change this to anti-diagonal projection, then we will see that when the lobe structure is changing. For the order 3 also, this lobe structure is changing. When we go to the right circular basis, in the right circular polarization, then the polarization, this lobe structure is also changing in single photon. And for left circular, that is where variation is happening. So basically, we are making a projection in one, we are making change in one photon. We are detecting the change in its partner photon, which is away from its. So it is in a non-local kind of process. So all those experimental results you can just put in this box pair, and then that variation is evident also in case of single photon. And this basically, just confirming us that using this classical beam, we can transfer directly this entangled photon or classical beam into that single photon, and then get that similar properties whatever the pump photons are having. Okay, and from here also we can just find out that when this entanglement from this entanglement witness parameter W, which is more than 1, that is basically just confirming it's a hybrid entangled photon state. Okay, so last one is another thing is we have always talked about this. Let's say if you have an input photon 1, order 1, and it's a transfer, then transfer it to 1. Now, if you have, let's say you have, instead of 1, you have a mixture of OM modes in the pump beam, and then can you just convert that one into the OM spectrum of the single photon? So that is basically something interesting, because you can generate then in that case a single photon source, a single photon with different OM modes, and that can be basically just basically for the multiplexing kind of or quantum communication one can use. So what we have done just to do that, this is the experimental setup. We have used a blue laser, and then using this blue laser and then SPP, or we have converted into vortex beam, and then this vortex beam we can make it into asymmetric. So we have measured the spatial structure of this, or the OM structure, OM content of the beam using special light modulator and single mode fiber. Then that pump beam, some part of the pump beam is going and passing through an nonlinear crystal, producing single photon pairs in a type 2 configuration, and then we are splitting into two arms. One is signal, another one is idler. And then again, we are making that OM projection using special light modulator here, or basically this projection technique is basically is a phase flattening technique, where if you have plus L, then you give a minus L OM or phase structure in the SLM, and then it will flatten and the phase variation of the beam. And if you focus it to the single mode, it will convert into the Gaussian mode and then get focused into get coupled to the single mode fiber. That is what we are just doing. This is one of the technique to detect the OM mode of the photons. So same technique basically using for all pump, signal, and idler. And then here we are basically, just to find out, it's an input OM mode, or the OM mode of the photon is unknown. Then we are basically changing the phase pattern of the SLM to different orders, and then seeing what is the coupling efficiency or coupled photon. From there, we are just producing the spectrum. So for the pump, we have measured. So when you have exactly order 2, then OM spectrum shows that order 2. When order 4, then OM spectrum is 4, or when order 6, OM spectrum is 6. That is what we expect. Okay, so it's a pure OM mode is there. Now, what we have done, we have basically just produced asymmetry by moving the SPP slightly away from the vortex, from the optics axis of the beam. So from the optic axis, we have just moved that SPP, and that has created that asymmetry in the beam. And in that case, we see there is, instead of order 2, we start seeing some other order OM modes in the pump itself. So if you keep on increasing this, the spectrum keep on changing, and then for different orders, you can see that the spectrum is there. This is what is the spectrum. So I have shown that asymmetry parameter 0.5, but we can just we have studied it for various asymmetries, and then the spectrum pattern is changing. Now, what do we do? Using this asymmetric vortex, we have now using this, let's say order 6, we have used order 6 and of the pump, and then biphoton modes, OM mode of the biphoton we have selected, keeping the one of the OM mode of this pair photon. Let's say signal OM mode is 3, then we are triggering that idler mode. So then you can see that in idler mode is almost, say, some value, because 4 is there, and then some pattern is there. But if you keep on increasing this asymmetry in this one beam, where the signal is carrying a different OM modes, then the pump is carrying OM modes, so then you can see that the partner photon is having a spectrum. Instead of a straight line here, we can see that one we see some additional OM content in that single photon. So, or like this one. So if you can enhance further, then this pattern is moving from here to there, and with a broad spectrum. So we started, that means simply by changing the OM mode of the pump, we can just create the single photons with the different OM modes. So with this, I come to the conclusion. I think I have just talked enough about the the research we are just doing, and I hope I convince you also it's very important and interesting for the advancement of photonics in general. And these are the some of the conclusions. I leave it for your reading, and for the best interest, I would like to thank you here and stop my talk and wait for the questions in case you have. Thank you very much.
Thank you. Thank you very much, Dr. Samant. So we would have questions now. Hello. So the session is now open for questions, discussion. So please feel free to come in. Hello. You may also type in the question and we can read it for you. So otherwise you can just unmute and ask it out.
May I ask?
Yes, yes, please.
Yeah. So, good morning. I'm Shobhana Chakraborty. So, thank you, sir, for a very interesting, wonderful talk.
Oh, thank you.
I was having some internet issues, so I do not know, because sometimes your voice was breaking because there was a problem on my side. I just need one little clarification. If I've missed it out, maybe you had said that is when we are doing the entanglement of a photon, so it is basically the two different states. Like suppose the orbital angular momentum of the single photon and the polarization. This is what you are actually trying to entangle, right? These are the two states, if I'm correct.
Yeah. It's a hybrid entanglement. It's a 2 degree of freedom is not separable.
Okay. So fine. So that means it's okay. The other thing that I wanted to ask, this is just a experimental interest. So using this idler, so you are generating the idler from single. You're from the single beam. You're generating the signal and the idler beams.
Yes.
Is that so, or are you using another laser for the idler?
No, it's in the parametric process. That is so these parametric processes are something very interesting. So you can have a single laser,
yes,
and you can generate all the wavelengths you want. So only one laser, and that you can divide into any, because the energy conservation, if you see that when omega p is equals to omega s plus omega I, that conservation law, this omega s and omega I, there is no bound for these two. Okay, so it can go. So let's say omega s is low, then omega I will be high, and vice versa, and then same. So basically, just there is no upper bound for this one, but the upper bound coming from the phase matching condition of the nonlinear crystal or the transmission window of the nonlinear crystal here being used. So basically, in principle, you can just generate any wavelength you want from a single laser. That is what we are just trying to say.
Yes, I think for using an OPO, you can easily do that.
Yes.
It's actually, why I wanted to know this, because I have done a few experiments on nonlinear optics, but we have used two different lasers. So we have used an OPO for the signal, and then we used a Tesaphier for the idler, where we were tuning the Tesa. So of course, we were not doing what you were doing. So we were just doing some frequency conversion processes inside Xenon. That was a different experiment, but this is what I wanted to know, because we were using two separate lasers because we were tuning the Tesaphier laser. And this was from the OPO, that is from the NDR 1064, and we just did the conversions, and then we combined the two. That's how I.
That's a SFG process kind of thing.
Yes. So here, actually, you're doing it from the single laser itself.
Single laser.
Okay, yeah, because that's what I saw in the experimental setup.
Yes, single laser, but we also do this on SFG process. That's two different lasers, and then add them to go for higher energy photons.
Yes.
like going to the UV, starting with this 1064 and then going to the 355. Means
Yes,
we
yes.
have to just pump up the energy. Or let's say we have also studied like from 2360 nanometer or 2.3 micron to 600 or 589 EOLO laser. From mid-infrared or near-infrared wavelength range to the EOLO one. That is something I have not shown here, but we have also demonstrated something like that. This is using two different second harmonic generation process. Basically, we are just generating fourth harmonic.
Okay. Yes.
So,
So-
means you can use any combination of the laser or single, double, or you can use also, let's say you have studied SFG, but alternatively people use also OPA, optical parametric amplification. So let's say
Yes.
amplifier there also most of the cases,
OPA was there inside our laser, inside our
okay.
laser. So it was
Yeah. So say TISA pair OPA system, Topaz.
Yes. So that was okay. Thank you so much.
Okay, thank
Would
you.
like to interact with you later on, so I'll
Please.
just take your email address and maybe.
Please. Thank you.
Thank you so much.
Yeah, further questions?
Sir, good morning. This is
Yeah,
Bhaskaran.
Yeah, good morning.
Sir, did you generate the zeta power? A laser, zeta power.
It's petawatt kind of lasers are now available, but people are just trying to push it towards that.
Okay, I think one zeta is equal to 10 power 21 watts.
21, yeah. That is the domain people are just looking. But petawatt is different countries are having that. In fact, India is also trying to build that petawatt laser system.
Okay, sir. Okay, thank you.
Yeah.
Okay, any further questions? Maybe we can have a couple of more questions before we. Okay, if not, then please join me in thanking Dr. Gautam Samanta once again for this really wonderful session. And
thank you very much.
so, and if in case you have any further queries or doubts, you can always email our speakers. So that's the thing. So yeah, thanks very much. Thanks.
Okay, thank you.
So the next session will be by Dr. Raghavendra Medisetti. But we will have a 5 to 10 minutes break, but only 5 to 10 minutes, not more than that, because the session will begin at 11:45. So you may drink a water or tea or as you prefer, but please be back at 11:45 for the next session. Yeah, thanks. At the same link. So as there's no confusion, the link is going to be the same for all sessions, all days. So 5.
Hey, Mohammed, how are you, man?
Good. How are you?
I'm fine. So, single-handedly handling whole FDP.
Uh,
Hello. Yeah. It's repeaters. Repeats actually.
It won't if I kill the sound or maybe.
Hello. Hello. It's better to kill. Let me see if I can share it. Hmm? So it's like 1 hour. You can go for 1 hour to 1 hour 15 minutes, something there, right? Okay, I will try to make it like 1 hour to 1 hour 15 minutes. Whatever the rest, I will try to take it into the session section. I'll go rather slow because I don't have many slides and it's completely advanced topic. Like it's a actually this is a postdoc work what I did. So it's not related to the FDP. I mean, like it's not fundamental actually. It's completely like to the research level. So let's see. So I'll rather go slow, but yeah, I will. We don't know how long it does take. Like I have roughly like 37 slides. But I will take slowly.
Yeah, too slow, and you can also maybe then say that if you have any doubt in between, then they can ask. Otherwise,
Oh,
you
that
can
would
ask briefly. You won't even make it interactive.
that would be nice. That would be nice and interactive. Do I need to switch on the video? My video?
Yeah, you share the screen.
Yep. But do I need to switch on my camera? That's a question. start video. All right. So you did your PhD.
Hello, everyone. Am I audible? Hello, am I audible? Okay, so we're back for this faculty development program, the next session for today. And we are really thankful to AICTE for supporting this event. And so on the emerging area of photonics. So for this next session, we have with us Dr. Raghavendra Medisetti from the Department of Chemistry at the Indian Institute of Technology, Bhilai. He's an assistant professor here. So Dr. Medisetti did his PhD from the National University of Singapore. And afterwards, he had a illustrious research career in Germany, where he was a Humboldt Fellow, and he worked at the Technical University of Munich, and as well as at the Ruhr University, Bochum in Germany. So his expertise lies in the fields of metal organic frameworks, coordination polymers, metal organic chemistry, and as well as on the photochemistry and photophysics of nonlinear optics. Those are the topics he is going to speak to us in this session. So we are really pleased to have him here delivering this session, and we are thankful to him. So without any further ado, now I would like to invite Dr. Medicetti to kindly deliver this session.
Am I audible to you? Hello?
Yes, sir, you are audible.
Yeah, great. Thank you very much. And yeah, before I start, first of all, I would like to thank Dr. Mahavir and Department of Physics, and as well as the AICTE to provide for inviting me to this talk and this FTP program. And I would like to, before I go further, I would like to inform you guys that, like, if you are interested, you can always stop me in between and ask questions. And basically, I'm a chemist. Okay, of course. I'm more into the synthesis, and then after that, I will come to the applications, specifically in the physics and nonlinear optics. So, given this scenario, I will explain the things from the chemistry point of view, and decent amount of physics also I will explain you. So if you have any questions or if you don't understand anything, feel free to stop me, and then I can try to clarify whatever I could, and then we can go further with the discussion as well as the presentation. Okay, I hope you are fine with that. And with this, let me start my presentation. So today we will be speaking about multiphoton absorption from the metal organic hybrids, specifically towards the metal organic frameworks and coordination polymers. So multiphoton absorption is one of the nonlinear optic properties, which I have been working for almost like 5 to 6 years, and is one of the nice opportunity for me to speak to the different audience, because I mostly speak to the audience of chemistry. So this is very interesting for me to start presenting my work to the different audience, such as like physicists. So I hope I will convince you guys with how a chemist can design the material for nonlinear optics, because I know like physicists are more into measurements and characterizations, but in the synthesis side, but as a chemist, I'm more into the synthesis and characterization and bit of into the application. So I fall into this region because of my to learn new things, specifically in the optics side. So with this, let me briefly introduce about the keywords such as like multiphoton absorption as well as nonlinear optics, as well as a metal organic hybrid material, especially MOFs. Then after that, we will go into the okay. Then so I don't think I need a strong introduction. So I'm not giving you very long introduction of this topic, especially nonlinear optics. Nonlinear optics, but I will be giving you very brief introduction about what is nonlinear optics. So if you plot a graph between the polarization energy, give me a minute. Excuse me, guys, just give me a minute. I hope my screen is visible to you. Yeah. So let me know if you can't see my screen. Okay. So if you are plotting, if you plot a graph between the polarization density as well as the electric field, and if it forms a linear line, then it is called basic linear optics. Where if you plot the equation of this, you can the polarization density, if it is directly proportional to the electric field, then it's called linear optics. But if you start increasing the electric field, okay, or polarization density, if then there is a deviation in this linear nature, then you start observing the higher order responses, and which typically called as nonlinear optics. To make it very simple from at least the multiphoton absorption point of view, you see here you are passing two lasers from a material, from a crystal, you can take it. And if the photons of these two lasers doesn't interact, and no interaction between the light beams, then it is called as linear optics. But when they start interfering each other, sometimes it can merge, it can break into they can be combined, they can be different, and there are a lot of methods could happen mechanisms could happen. And based on this, we call it as nonlinear optics, because the photon is interacting with another photon given the scenario of crystals or the solid matter interaction, photon matter interactions. Okay, so in case of multiphoton observation, what do we expect? You have two photons are combining because within the solid matter interaction, then you produce a new photon and produce a new photon, which is the combination of these two photons. So it's you are combining the two photonic energies and producing a new photon. This is the typical phenomenon of multiphoton absorption, and this phenomena is used to increase the energy of the photons, and specifically into the IR radiations, where you can combine the two IR radiation and produce the visible light. Okay. And of course, designing such kind of material is going to be the topic which we will be talking in today's lecture. So if you plot the same thing in the Jablonski diagram, you see like in the most of the times you observe one photon fluorescence when your material is absorbing only one photon, which have high energy and produces a lower energy photon. But once you have more than two photons, either two photons, or three photons, even four photons, which we'll be briefly discussing today also. So when a material can absorb more than two photons, then still emit the higher energy in case of this, because like you are breaking the your photon energy, which has been broken into two sections because it is absorbing two photons, are broken into three sections, which is three photons, and produces the fluorescence, which of higher energy, so that like you get multiphoton absorption. Since this energy is like either half or one third or quadrupled, like one fourth of it. Because of this reason, the energy of the excitation and the energy of the emitted will be hugely different. Mostly like excitation is a lower energy and emission gonna be in the higher energy. And how do we know that it has absorbed two photons or three photons or four photons? It can be easily understood by plotting the graph where the rate of the n photon absorption, if you plot in the graph between the absorption as well as the emission, then you could see you can obtain a plot with a slope of the is n actually, n power slope of n actually. Of course, I will be also presenting this with some experimental data so that you can understand better in this one. And specifically, if you come to the quantification, because you know, like you have n number of materials in the world. So how do we characterize which material is good for your phenomena? In such cases, to quantify it, we do use the two photon absorption cross section, which is noted as a sigma 2 Pa, and it is named after the units of this one is named after a Nobel winner, Goppert Meyer, and who has hypothesized this phenomena in 1950s and 1940s, and she received the Nobel Prize in 1950. And because of her contribution, it was the units has been named after her. And this is literally known as like a two photon absorption cross section, TPA, two photon absorption cross section. And the units are either like Goppert Meyer, or if you want to take it into the MKS units or SI units, you can say like fourth power of centimeter into second and photon and per photon per molecule. So this is the basic unit. And this is typically of the two photon absorption cross sections. Okay, but practical terms, two photon absorption cross section is not that valuable actually. Most often, if you want to get a material which is like very good absorption cross sections, sometimes it's tricky to obtain, first thing. Secondly, it's not that applicable. So most of the people like us, we always try to use the MPA brightness. Multiphoton absorption cross section, action cross section, we always call it, or just simply call as brightness, which is the multiplication of the absorption cross section as well as the quantum yield of this material. And this gives you how strongly the two photon excited fluorescence can observe from the material. Okay, and if you have if you have very good MPA brightness, it is expected to show. It is expected to show better applications, especially in the imaging, imaging of the materials. Okay, imaging of like bioimaging, or if you want to use some application like optical based applications, you can they are mostly used actually. So this is about the multiphoton absorption, and then next we come to the metal organic frameworks or metal organic hybrid materials. So if you look into the metal organic frameworks or coordination polymers, they are also known as the coordination polymers. So these are the typical hybrid materials which are between the organic polymers and zeolites. I hope you know brief idea about the organic polymers, where you have like organic monomers are combined polymerized into long chain polymers, and this is a purely organic based system, which includes carbon, hydrogen, nitrogen, sulfur. These are the base and oxygen. Now, no other element usually expected. There are no metals in the system. This is called organic polymers. And if you come to the inorganic materials, I'm taking as a zeolites or metal oxides. So these are the another kind of material where you don't have any inorganic material. Any like they're typically of inorganic systems, which includes like nitrogen, oxygen, sulfur, and phosphorus based systems, but you don't have much of organic in these systems. So when you combine organic monomers with inorganic metal nodes, so like either metal oxides, metal phosphates, then this there are different materials and different methodology we use it, and then you combine them and form a hybrid material. They are called as coordination polymers or metal organic frameworks. Yeah. So why I'm taking the zeolites? The reason for the zeolites we have in this example is because of these morphs are known for very strong porosity. So they have a huge amount of vacuum, empty space, which can be used for various applications. So if I wanna give you a brief introduction about the what is a morph in this pictorial view, you can see here. So you have a metal node or metal cluster, which you can see from the red ball, and these are coordinated by organic linkers, which is like a yellow stick here. You can see here. When you combine them, you can form a framework structures. See here, so it's like you have a framework structure with a huge empty space. You see here there is a white space in between, right? That's completely empty space, which can be used for various applications. So do you think like does it mean like it's always you produce the same structure, which is like which is called as alpha polonium, we call it actually, or cubic, where you see here red ball is coordinated by 6 linkers, and the yellow stick, which is the organic linker, is bonded by the bonded to the 2 metal nodes. Is it only like this mechanism, or is it only we can get the only one structure? Actually, no. That makes it, this chemistry is very interesting because you have a very good controlling of the structure as well as the dimensionality. So it's like you can produce one-dimensional polymers as well as the two-dimensional polymers as well as three-dimensional polymers based on the your metal node as well as the organic linker. So if we take, let me take some examples, like such as like you have connectors. Either it can be connector is nothing but a metal node here. So it can be bonded to the 2 linkers either in a linear manner or an angular manner. Okay. Similarly, you can have the number of metal node can be have the coordination geometry of T-shaped three. It can be coordinated by 3 linkers. Either it can be, and that too has a different geometry such as like T-shaped, trigonal, planar. Similarly, you can go to the four coordination geometry, which is square planar and tetrahedral, and square pyramidal in case of 5 coordination geometry, as well as the octahedral in 6 coordinate geometry, and there are many more. So, but I don't want to go into more on details. Similarly, linkers also can be either like linear linkers or bent linkers in case of ditopic. Ditopic means it's bonded to only 2 sides. And you have linkers even like a tritopic with a planar, square planar, and tetratopic. And even we have the linkers, which is like hexatopic. And this is a very broad view. I would like to give it to you. And by looking at this, I believe you can realize what are the permutations and combinations you can make it. And you have And you know, like in the periodic table, we have so many metals, right? And literally, so far there are coordination polymers as well as the morph in almost all the metals in the coordination in the periodic table, as well as there is almost unlimited number of linkers are available. So by combination of these, you can produce materials as widely as possible, as like unlimited. And this field of research started in early 1900s or like late 1990s, and so far it's almost like 5,500,000 structures has been reported in the literature. You can understand 500,000 structures are reported. Okay, so it's only a tip of the iceberg. There is a long way to go. Okay, and since we have a huge amount of control of the structures as well as the functionalities, because whatever the linkers you take it here, you can control the functional groups over that. Functional group means either like hydroxides or amines or so and so. So you have hydroxides, amines, so and so by so that you can control the functional groups and properties, as well as you can also use different metals where the metal comes with like some kind of conductivity, and sometimes they come out like insulation behavior, sometimes they come with a magnetic behavior. So you have a wide number of applications as. So if you look into the maps, you can see here the application of these materials has been like into the gas storage. As I said, like there are huge amount of porosity, so they usually start, and the whole field of research started with the gas storage actually. Later it went to the gas separation and followed by catalysis, and later it's like exploded into almost all the research areas in the recent years specifically, where they have been taken into the NLOs, and conductivity studies are the most dominant in the research current research areas later, and they are also established very well into the sensing applications as well as luminescence and even drug deliveries, and there are n number of applications. Of course, there are still large scope to explore further. So this is typically due to the like highly controllable molecular arrangements, as I have briefed in the last slide, and these are also commercialized into the these are have been already commercialized by BASF and Signal Rich. So you wanna get them, and you can easily get them. And as I say, like these are like very interesting because the huge amount of porosity, right? If you to brief you about their importance, the highest amount of surface area in the material world is from Mars. What is the value? Is roughly around like 10 to 12,000 square meter per gram. The value of the surface area is like 10 to 12,000 square meter per gram. Whereas if you take it to carbon black, the best quality of carbon black only produces 1,000 square meter per gram. But if you look into the map, almost more than 10 to 12 times higher. This literally shows you the importance and applicability of these materials. And here are the two famous maps where which have been reported in 1998, which brought the main focus of this field into the like huge number of researchers. These two maps attracted more researchers to work on this field, where you can see that this is like this is a ballistic diagram of these compounds, which is called as HKUST. It is first produced in the Hong Kong University of Science and Technology. And that's where like they named it as a HKUST1, which is which they use a copper metal as well as the organic linker like a benzene tricarboxylic acid, and produce a framework structure here. And you see here there are two different kind of pores. What do we mean pores? You can see here there is a yellow ball, right? This yellow ball is nothing but the empty space available in the framework, in the structure. And as well as like there is an orange ball, which is also empty space available in the structure, which is, but it's a different size and different environment. Same goes with like MAF5, metal organic framework structure 5, and these also have a huge amount of porosity, which you can see from the yellow ball. Okay, so you see, we always look for the biggest yellow ball so that we can get the more porosity, more absorption properties, at least in the early days of MOM. But recent days, it's not necessarily we want to have the high porosity, but we want to get into the specific applications such as NLO, which I'm very much interested in. I have been working for almost like 5 years, where we don't mind about the porosity, but we rather focus on how the molecules packed. And unlike one more important thing I would like to highlight here is like, unlike most of the organic materials which are soluble or which show the optical activity, very strong optical activity only in solutions, unlike them, our MOFs are insoluble, which is a huge advantage because like if you wanna make a device out of it, for example, if you wanna make laser, you don't wanna have a laser crystal which is soluble in water, like if you dip into the water or if you by mistake if you bring into the like hygroscopic environment or by chance if you bring it to somewhere where you have ethanol or sanitizers, if you have a lot of organic solvents around, and if you don't want to have a material which is soluble in that place, right? And that place, our mass gonna be huge. This material gonna be huge applicable, hugely applicable. And secondly, and you know, like most of the organic compounds, they are very good in, especially dyes, they are very good in diluted solutions. But once you solidify them, they are not good. Not always, but most of them. Why is it? Usually, once they pack in the solids, there is a like a non-radiative pathways going to be enhanced, and the optical activity going to be reduced. But in case of these, our frameworks, metal, since these organic linkers or dye molecules are bonded by the metals, they are very rigidified, so non-radiative activities gonna be reduced. So like optical activity is significantly enhanced. Sometimes even we even achieve the quantum yields of the compounds up to 1. So you can imagine you can produce a solid state material with highest quantum yield properties as well as the high, which I'm going to discuss about like in case of multi-photon absorption. They are also very strongly almost all the fields of solution dyes, overcoming almost all the dyes and many more. So with this, let me go into the next slide where how we characterize these multi-photon absorption, followed by some. I will give you examples of it. So most famous example how we estimate the multi-photon absorption cross-section is this scan method. I hope some of you might be aware of it. So this is a very brief schematic. When the laser beam is coming, then you have the bands like a partial mirror where you can see like there is like there is a kind of a partial passage where you see here a reference detector as well as the light is passing through a lens, and you get like focused and then defocused. Again, you put a like a beam slit, and it will be separated into the one of the beam gonna be towards the CA detector and OA detector. Okay, and where this place where your sample is located, which is where the focus is going to be 0, z is equal to 0, then it will be moved from minus z to plus z. And during this time, we will be estimating how much is the values of like intensity values at the closed apertures as well as open apertures. And if you look into the plots, you see here in case of closed apertures, it will form a sigmoidal plot like this, as well as the another one is like Gaussian inverse Gaussian curves such as this way. Okay. So, but here this is a typical architecture or typical setup where we start measuring the absorption cross sections. But this has a limitation. So literally, you see here light is passing through the sample, and you're only calculating how much transmittance has been observed. But as I said in the previous slide, our compounds are not soluble. Even if you make it to the micro and nanoscale, our compounds are known to scatter a lot. So there is a huge amount of scattering happens. So the transmittance is not really user transmittance, rather like you use a fake values as well sometimes. So this kind is only good when your particles are like when your compound is completely soluble, or your particles are very little scattered effect or non-radiative pathways, which could happen in this. And only in such cases, these kind of methods are used. So since this is not very well applicable to us, then we had to fabricate, we had to design and fabricate the new methodologies and new systems to calibrate our multiphoton cross sections. In such cases, we started using, instead of like a transmittance, we started using the fluorescence mechanism. Of course, I hope you remember, you understand that absorption and fluorescence more or less gives you similar values. Of course, not always same, but these, at least our experimental point of view, we felt and we observed the values are very good. And that's where we started up, and instead of going to the transmittance, we started working towards the fluorescence mechanisms. In case of this, what do? We again here also there are two different methodologies. One is the solution or dispersed state mechanisms or methodology, or other one is the solid state methodology. In case of solution or dispersed state methodology, what do? We take the compound and we take like microcrystals of the MOF. Then you disperse them into the a solution which is having the reference. In case of this, you have a MOF and you have the rhodamin B as the reference. Then you exit the compound and you collect the fluorescence of the compound either in the backscattering collection or perpendicular collection. And your collection going to be look like this, where you can integrate the MOF signal and as well as a reference signal, and then you plot the data in the equations which I'm going to be describing in the next slide. So this is one of the methodology we observe. And second methodology, we work with like sometimes I don't want to dissolve my compound. Why? Because our compounds are porous, where the solvent can go in and it does influence the optical activity. I will also explain that in one of the example in the coming slides. So such case, and since it is affecting the optical activity, you may not be able to get the its nonlinear absorption cross sections exactly from the naked framework. Rather, you get the solvent influenced frameworks, which we don't like it. In such cases, we start packing the compound in a between the slides in the under vacuum or under argon conditions based on the requirements. Then you compare the fluorescence intensity of the solid along with the reference, and then you plot the graph in the following equations. So if you look into this naming, it's like the first one is going to consider as IST, internal standard TPEF, 2 photon excited fluorescence, in the where you have like a rhodamin B acts as an internal standard, and where you're estimating the 2 photon excited fluorescence, and then you try to calculate the absorption cross sections. If you come to the solid state, you see here you don't have any internal standard, rather like you have external standard, such as like you compare, you measure the value of the compound in the solid state, like you pack the compound in the slides and you start collecting it along with your reference, then you compare them. So during this method measurement also, we usually pack the compound and then you start rotating the sample. Why? Because you are exposing your compound to the laser. Of course, and specifically very high energy lasers. So there may be, not necessarily always, there may be chance that your compound may be decomposed if you are keep on exposing it. So once you keep rotating it, the possibility of decomposition is going to be reduced, so that you get and as well as you get normalized information. So this is a typical setup we work with. Okay, and if you look into the equations of calculation of absorption cross section, the fundamental equation looks like this, where you see here intensity of the fluorescence is dependent on concentration of the molecules and intensity of the excited light and refractive index, because you have a solid state, so you have a refractive index. And this is the where we start seeing the absorption cross sections and quantum yield as well as the collection factor. So all these factors will be influencing it. So if you want to calculate one sigma 2 or sigma 2 into absorption cross sections, either absorption cross sections or absorption cross section, which is a multiplication of sigma 2 as well as sigma quantum yields. So to quantify it, you need to have so many parameters, which is sometimes very difficult to measure in the laboratory for every material. Say like, as well, we have more than 500,000 compounds. So if you want to calculate these values for 500,000 compounds, it's almost impossible in the at least a couple of decades. So what did we do? That's where we started using the reference materials. Reference are the materials which are well established in the literature over the several decades. Last at least more than 2 decades, they have been taken the references such as like beryllium, rhodomin B, cadmium sulfide, cadmium selenide. These are very good nonlinear optical active materials. So they have been established, and we taken since we have the absorption cross section of these values as well as quantum yields. So if you measure the absorption intensity of the 2PEF for the sample as well as the reference, then it is easy to observe sigma, easy to calculate the sigma 2 of the sample. Why? Because we consider the concentrations are going to be cancelled out because we are using the same reference sample or so on, as well as the intensity of the excitation is same. Yeah, we expect the refractive index is same, and since we are using the same setup, we can use the same collection factor. So all these are going to be cancelled out. Then we get the we can easily calculate the sigma 2 of the sample very easily by using these comparison methods. So this is a typical methodology used for the calculation of 2-photon excited fluorescence. So if you look into the literature, the first ever report which presented multi-photon absorption cross-section was in 2015, which is again from my from the group where I worked as where I finished my PhD from J.J. Whittle group, and where we have been hugely focused in the recent years, where you take the MOF, and this is the typical MOF as you can see here, where you have the zinc, this is the molecular formula of this compound is like the zinc. Zinc is the metal node, and where you have a stilbene dicarboxylic acid as the linker. You see here, this is the zinc as a metal node, and where you combine this zinc node is combined by the organic linker like this here, and forms a 2D layer structure. So zinc, SDC, zinc, SDC, zinc, SDC, zinc, and SDC. So you see here, it's like a one 2D plane. It is continuous actually. All the 4 directions actually. All the 2 directions. It is continuous. Then this is the same layer can be observed in the below as well. Okay, and these 2 layers are bridged by the another linker called as this anthracene dipyridine linker. Okay, so since it's like a layer structure which are pillared by these linkers, this is called as pillared layer structure, we call it. Okay, and this is a basic structure. This is a basic chemical formula, and upon excitation of this compound under lasers, it shows a very good nonlinear activity, and of course, this is the first paper. It has been shown multi-photon absorption, and which shows the action cross section of like a value of 1.6, and later where a lot of different organic molecules has been loaded into the frame, where you can see here one is the pyridine here, which is compound called as 2 we call, and another one is anthracene. So you see one anthracene has been incorporated into the framework, and all these compounds shows upon loading of the different dye molecules, there is enhancement in the absorption cross sections or action cross sections actually. Okay. In case of this, of course, we use the reference material as from beryllium, and the action cross sections are from like 1.6 to 7.2, and this is because there is a kind of a push-pull mechanism where the energy from the like electron cloud and polarization of the framework can be enhanced by using guest molecules such as like penicillin and anthracene, so that you can see like almost one order of phase enhancement is observed by loading the guest molecules. In addition, when you are exciting it, this anthracene also kind of get polarized and charged, where you see here the anthracene produces anti-radical intermediate that also helps to enhance the charge transfer or charge polarization in the framework. That also helps. That is the prime reason where this compound shows a very good, very decent multiphoton absorption, multiphoton active material. Okay. So these are the plots where you can see their projections by using from these materials. And how do I know, like, it's not only, these materials not only shows 2 photon absorption cross section, it also shows 3 photon absorption cross section as well as 4 photon absorption cross sections. How do I know that it's showing 2 photon or 3 photon or 4 photon, right? It is very easy. So you plot a graph between the power, logarithm of powers versus logarithm of intensities. Then you see the slope of this at different powers, and if you start observing the intensity of the fluorescence, then you start seeing a linear lines, linear like plots, and the slope. If the slope is the slope gives you the number of photons which are involved in the process, such as like if you see here, the slope of this curve is 2. Then there are 3 different compounds, so like almost all the compounds show the slope of 2. So it is absorbing, it is the material is absorbing 2 photons at a time. When if you go into the next plot, where you can see here, and this is like okay, here is the lambda excitation going to be like 800 nanometer with an initial intensity of like 1.8 gigawatt per square centimeter. Then when you go into the next level, which is like lambda max going to be like, when the lambda excitation going to be like 1200, which is expected to be like 4 photon, 3 photon, where the slope you can see here, logarithm of intensity versus logarithm of fluence or excitation, where the slope you can see 3. And here you see here, the intensity required for this is almost like 10 times higher. So you see here 1.8 gigawatt per square meter we used, whereas if you come here, and since it needs 3 photons at a time to absorb, so the same amount of photon fluence you need to provide to the system. Where you see here you are using 14.5 gigawatt for this actually. Just give me a minute. Yeah, sorry. Similarly, like you can also see like 4 photon absorption, which requires like where we are where we have like excitation is up to 1500 nanometers with a excitation energy of like 26 gigawatt or 18 gigawatt based on the material and its activity levels. Okay, and this not only the plots, and these are the microscopic images where you can see compound 1A, compound 2, and compound 3. How even at even at like 1200 and 1500, fluorescence can be decently observed. But once you come, but as you see here, from 800 to 1200, the fluorescence intensity is reduced, and 1200 to 1500, the fluorescence intensity is reduced, because in case of 800, only 2 photons at a time need to be absorbed, and in case of 3 photons to be absorbed at a time, and 1500, 4 photons have to be absorbed. And this is not very straightforward. It's very difficult to observe. And thus you see here just pure linker. So if you look into the linker, only just pure linker, if you are working with, it is only active up to 2 photon or 3 photon. But that is also very the intensity is very limited, very low. But if you come to the 1500, it's almost 1500, which is nothing but like 4 photon absorption. It's almost not active at all. Okay, same goes with like same goes anthracene dipedal system, where you see like 4 photon, it's decently active, but as you go to like 1500 nanometers, which is like 4 photon, it's very weak active. Okay. This is the first material which shows the multiphoton absorption in the MOF actually. But let me highlight that although it's the performance is decent, which has like a 7.2 Gepard-Meyer action cross section, but its values are not that great. So how to improve it? So this was the idea where we have been working on. Then later I started working on little different dye molecules. In case of this, we started using AIE dye. AIE dye nothing but aggregate induced emission based dye molecule. Okay, so these molecules are known to show better activity in case of restricted conformation. Why? Because like you see here in the solution state, these phenyl rings are keep on rotating as a rotors, and which leads to the non-radiative pathway of decay in the excited energy. And when you coordinate with the metals, this rotor motion of these phenyl rings get reduced so that the optical activity can be enhanced. As well as there is a conformational change. You see here the angle between these phenyl rings as well as the olefin rings going to be changed based on the atmosphere as well as coordination geometries or coordination metals. That also influences the charge polarizability of the material, which we will be discussing in the coming slides. So more or less, I started working on this AA dyes, and then I started combining with the two metals where like zinc and indium has been the metal nodes, and then combined and produced two different structures which are in different topologies, such as like the DMD and TFA, which are very new actually those days. And we have obtained the framework like this, where you see here decent amount of porosity available. And then we started observing the multiphoton cross section of these values, which is up to like 3000. You imagine in the previous slide, I have been discussed about the absorption cross section values of up to like 7.2 Gepard-Meyer. From there, we have obtained the Gepard-Meyers of like 3000 Gepard-Meyer, which you can see like almost 3 orders higher. Okay, that is in case of like indium MOF. Whereas if you come to the zinc, you get up to like 1000 Gepard-Meyers. One interesting observation we did observe is like this MOF, especially indium MOF, is very porous. You see here huge amount of porosity available here. Since because of the such high porosity, if you are removing the solvent from the framework, okay, the empty space in this framework is not sustaining the framework, then it starts the crystalline is going to be lost. Like there is a deformation in the structures, and then the framework is going to be lost. Crystalline framework loss is crystallinity, and otherwise long range harder has been reduced. Then instead of these compounds are very crystalline, and these crystalline compounds convert into non-crystalline or amorphous compounds. So during this, you can imagine the framework. In the framework, molecules are, especially in this case of structures, they are far apart and they're well bonded by the metals. But once the framework loses crystallinity, the linkers coming closer because there is an empty space available. So the linkers move closer, and in this during this closure, the molecules are coming closer, and there is a lot of mechanisms could happen. During this process, the absorption cross-section values got reduced almost three times. You see here, when it's a framework structure, very high crystalline, it's almost 3000 Gepard-Meyer. Once it is converted into the amorphous, where the loss of TPA activities upon decreasing the crystallinity, where like we are removing the solvent, then it's almost three times lower than the value of crystalline structures. This is very interesting. So this is the one way we can prove that we can tune the nonlinear activity by using different same material but different mechanisms, where you reduce the crystallinity so that you can reduce a nonlinear activity. And again, you can introduce a solvent, then the crystallinity get enhanced, and then your whatever the lower intensity multiphoton will convert back into the high NLV active material. So you can tune the properties. And here also we have observed, these are only the values at 800 nanometers. Okay. Then we have calculated the different wavelengths, and sorry, this is not at the 800 nanometers. This is rather at the 650 nanometers. Sorry for the mistake. But like you see here, at a different wavelengths, we have observed different absorption cross section, which is very similar to the UV visible absorption cross absorption. Actually, they are actually rather shifting towards the higher wavelengths. Actually, that's it. Okay, and then then as I said, like these multiphoton cross section values, multiphoton activity of molecules are highly applicable for last 2 decades. Then we try to compare with almost all the kind of materials. So take it like a dye molecule such as like rhodamine B and rhodamine 6G, as well as fluorescein and coumarin, and then some of the polymers and porphyrins. Again, compared to them, again these are very good. You see here, these are the values of ours, and there you see here they are values of others. But once you come to the porphyrin, which are making to the layers, 20-layered film. So this is the one of the material which shows almost comparable value to our values. However, if you increase in the different more number of layers, the often is getting reduced. Then of course we did compare with like a content that's such like cadmium selenide, cadmium telluride, and zinc sulfide, manganese dope, zinc sulfide, and so on. Compared to almost all these materials, our compounds are showing the best activity in the literature. Okay. Then, by looking at this, actually, this was like this is the kind of like we started designing it, and we try to make the material, but it is the whole design strategy is like a little bit of half cooked, because we don't really know how to design it. Then we started working on it, because we want to establish the mechanism of measurement rather than the designing the material. Actually, the first focus was how to measure it. That was a huge challenge during my work. Okay, once I established, then I started working on the material designing. So how do we design a material which shows a very good performance and very good activity? That was the focus of it. So for that purpose, we have taken the basic principles of designing the compounds, specifically organic molecules or metal organic systems, which are established last 3 to 5 decades. There's huge principles are established in the field, but they are mostly derived useful only in the solution states. But I want those basic principles into the designing of these maps. So further during this process, we come up with a criteria such as this way, like the compound should have dipolar or multipolar in nature. Either it can be like a donor acceptor, donor by acceptor, or donor by acceptor, donor acceptor donor, or acceptor donor acceptor. So we had to have multipolar systems. This is the first criteria we try to adopt. Similarly, secondly, we want to work with like long conjugated planar molecule. Why is it? Because these once you get the polar ends, we want to differentiate this like a polarity. We want to enhance the polarity so that like if you have long chains, we expected this charge separation to increase this. Thus, we could establish better value, establish better materials which have better activity, multiphoton absorption activity. Similarly, we want to have good fluorescence quantum yield as well as a better separation of 1 photon, 2 photon bands. The reason is it's more of experimental point of view to easy to collect the signal as well as the easy to separate the absorption, 1 photon absorption and 2 photon absorption. Of course, the last one, as you know, like MOFs are the one frame. These are the framework material which can be where the solid state materials can be easily designed. So you can design conformations in various space. You can design these materials in the 3-dimensional arrangements, such as like what kind of arrangement you want, and once you get a different arrangement, what kind of aggregation you want, how far they want, and what is the angle between them, all the linkers, all this can be controlled well in the frameworks, and we want to utilize these principles in this one. And this is a basic designing criteria. But while we're designing it, we also questioned ourselves, like why we need MARC first of all. As I said, like it's a very simple. As I informed, these are the solid state materials, unlike the liquid states which are established in the literature, and compared to the organic molecules which are well established, as well as the quantum dots. Okay, these are they have very low chemical, thermal, and optical stability. But whereas if you come to the MOFs, they are very good in both chemical, thermal, as well as optical stability. So, do you say, like, being honest, do I say like these are the best material to show these properties? Actually, no. The best material so far, according to my knowledge, are like oxides. Okay, these are the best materials, but of course, our MOFs are in between the organic materials as well as the inorganic material. The stability, properties, everything is if you go to the like one of the first slides, you see here they are different. They are between they are sandwiched between the organic systems as well as the inorganic materials. This is the basic way it works. And the last choice why we want to come to the MOF is like tunability and you have a huge number of choice. So we have the basic design criteria such as like 5 design points, but basic one is going to be like only 2. The rest are like more of these 2 are more of like a measuramental comfortness, and the last one is we are still very new for it, but like we did try something out of it. Okay, so to design this criteria, we have taken the zirconium and hafnium based MOF. What do I mean by zirconium based MOF? So you know, like you have seen the one of the earlier picture where you have like red balls and yellow sticks, right? So red ball metal node, instead of like unique just metal, we use metal oxide clusters. Either it could be zirconium oxide clusters or hafnium oxide clusters, which can be coordinated to the TCP linker, which is the structure looks like this. It's the same structure which you see in one of the previous slide, which is AE dye, where the carboxylic acids are bonded to the oxy clusters and forms a framework. Okay, and that these oxy clusters have the 12 connecting nodes. If you come to like one of the earlier slides, you see we have talked about up to 6 connecting nodes. But if you come to these metal oxide clusters, it has 12 connecting nodes. So we can, by using the specific mechanism, you can control how many coordination sites can be bounded. So by using experimental conditions, you can do it, and we did that. And along with that, we also use different substituents such as like hydroxides and trifluoroacetates. Why trifluoroacetate? Trifluoroacetates are one of the strong electron withdrawing groups, so that the charge polarization in the framework can be enhanced if you are incorporating trifluoroacetates. Okay, so by combination of 2 metal oxide nodes and 1 organic linker and 2 different substituents, we have prepared 6 zirconium and hafnium MOFs. And during this, we have prepared 2 different structures. One is cubic. As you can see here, it's a cube. Where if you take a cube, all the corners are located by the metal oxide clusters, and the faces are occupied by the linker. And the second one is Kagame lattice, where you see here all the red bars are going to be metal oxide clusters. These blue sticks, blue architectures is like linkers. Okay, so when we are combining this, and by controlling the structures, you can able to produce different structures. And one more thing I would like to highlight here is like in case of cubic, this metal oxide clusters has 12 connecting nodes, right? All the 12 connecting nodes have been bonded by the carboxylic acid. Then only you can get the cubic. But if you come to the Kagome, it's only 8 connecting nodes. So you have still 4 more connecting nodes, and these 4 more connecting nodes are substituted with the different substituents. And by using this, we have produced 6 structures. Okay. In case of since all these in case of zirconium cubic structure, all the TCP linkers are bounded by the zirconium TCP. All the coordination sets of the zirconium are bounded by the carboxylic acids of TCPE. Then you produce a 12 connected node with the cubic structures, as well as the same with the hafnium structures. So these are the two modes of 12 connecting node. But you have 8 connecting node, which typically is the Kagame. In case of this, in case of zirconium, you have that trifluoroacetate as well as hydroxide, which is going to be 3 and 4 respectively. Similarly, if you come to the 5 and 6 comes hafnium connecting nodes, hafnium frameworks, where you have the 5th one is like a trifluoroacetate and followed by the hydroxide in case of hafnium structures. So this is how we made a node labeling. And then, yeah, so far we have able to obtain the different 3-dimensional arrangement, and you have different substituent. Based on the different substituent, you can charge polarization can be modified. Meanwhile, we are using 2 metal cluster nodes. One is zirconium and one is hafnium. Why should we need 2? The reason is zirconium is very high electropositive nature, so the charge polarizability of zirconium is much better. Zirconium framework is much better than the hafnium. Okay, so somehow because of this, like we have able to produce it. Then we did do some calculations before we go into the measurements actually. So in case of charge transfer or charge polarization ability, we took the 12 connecting node, where we have observed from the framework to the metal node. You see here, this is a framework organic linker, and this is the metal node. In case of cubic structure or 12 connecting node, 1 electron has been charge transferred to from the linker to the node when it is in case of 12 connecting. But if you come to the 8 connecting node, it is increased by increase it to 1.2 electrons. So charge polarization is much better in case of Kagame lattice compared to the cubic structures. So the idea of the 3-dimensional framework, why we need a specific packing, I hope you could realize, like by changing the connecting nodes, we can also expect different charge polarization. Then we started, in addition, you see here, in case of this, the conformation of the linker is different compared to the Kagame lattice. So the conformation, what do I mean by? You see here, in case of cubic, which comes under this level, where the distance between this carbon to this carbon is around 15 angstroms, and it is going to be showing the conformation over here. As you can keep on changing the distance between this carbon to this carbon, you see here it is keep on increasing from 12 angstrom to the 19 angstroms. The conformation strain is increasing and charge polarizability also changing. You see, in case of this, in case of cubic, where the CC distance, carbon to carbon distance is like 15, it has the highest charge polarizability. Whereas if you come to the 17, which is going to be Kagame lattice. Any question? I think it's by mistake. Yeah, Mukesh.
Yeah. Sir, I wanted to know, in the normal condition, the single photon absorption take place. So why does the multi-photon absorption take place? Please explain quantum mechanically.
Okay. Quantum mechanically, being honest, I'm not an expert into that direction, because I'm basically a chemist who is interested in this point of. But quantum mechanically, it might be because of charge polarization, and there is a possibility of the framework is enough. The structure may be good enough to absorb quantum. But I am not much into the mechanical point of view, because I am more into the synthesis and application point of view. Hello.
Okay, sir. Thank you very much, sir.
Yeah, but here my focus was more about how to design the materials and what are the of these materials, because I am only currently discussing about how to tune it. I'll have to come with the applications of it. What's the theoretical background of it? Now the focus of this presentation.
Okay, sir.
I hope you understand.
Okay, sir. Thank you.
Yeah. So you see here, as you change the confirmation, I think it's like an echo is from other side. As you change the confirmation, the charge there is a strain and there is a charge polarization takes place, and because of this, you see here the compound which has the zirconium, which is a more polarizable nature and better charge transfer because of your 8 connecting nodes. This compound showed highest ever multiphoton absorption cross section in the literature those days. Okay, which is up to like a 3600 Gepard-Meyer, and of course by different substituents, different by from here to zirconium to hafnium, the value has been reduced, so we can tune it now. And by here is trifluoroacetate, and here is gonna be like sorry, this is zirconium, and this is gonna be hafnium. You see here almost like a 1/2 of it. And by removing the trifluoric acetic acid to the hydroxide, you see here almost like decent amount of decrease. So literally what I'm trying to prove it here is like we can now design a material with for a specific value of absorption cross sections and activity. So this is what we have proven in the early stages of research, where the first paper was published in 2015, and in 2017 we started producing the material which can be designed. That was a great achievement actually. Of course, we did calculate, we did measure the different wavelength dependent absorption cross sections, and which shows up to like a 2 photon and 3 photon and 4 photon absorption cross sections, which again almost all the three values, this is the highest in the literature, especially in the solid state materials. Okay. Then, and we also compared these values with again the literature. We are one of the best. So there are like dendrimers which are better than us, but still these are not really. They have their own limitations compared to ours. So we don't want. So more or less, in this work, until this work, I have shown the structure property correlation and controlling unpredictability of the material by using charge polarization and conformation strain to produce a material which shows a very good multiphoton activity. Okay, then later we want to work little more during my postdoc, where I was doing my work in TEM technology. Then we started preparing pillar layer structures, same one, but these structures are not like rigid structures where you see before. So we have used almost same linker, and instead of the then by coordination of this linker with the zinc metal, then you produce a pillar layer structure. You see here pillar layer structure where the layers are bridged by the linkers of this molecule. Okay, then when you are activating this material, the framework, this framework has advantage like they get slided. In other words, slided as well as contracted. As you can see here, pillar layer structure, once the layers are moved, when you are activating thermal activation, then the layers distance between both the layers is going to be reduced. So now I can control the distance between the different active dye molecules, which is TCPE, and then we try to compare these values. Not only this, as I said, these TCPE, these molecules have the like phenyl rings which are continuously rotated. They continuously rotate. But once you contract, we have proven that once your pillar layer structure, when it is moving from the pillar layer to the contracted structure, since the layers are coming closer, the rotation of this phenyls got reduced, which means your thermal relaxation is going to be reduced, which also helps in the enhancement of optical activity as well as non-optical activity. So during this process, we have shown the absorption cross-section values of this framework can be enhanced by 2.5 times by contracting it. Like, so you remove the solvent and you bring the molecules closer. You see here the optical activity can be the nonlinear optical activity can be enhanced by more than 2.5 times. And these are the values you can see here. It's a pink and blue color. Blue color are the graphs where you have values of absorption 150 is converted into almost 400. So you can understand how well the optical activity, nonlinear optical activity has been enhanced. But is it like always there? Actually, not necessarily. Of course, it depends on several other factors, but this is one of the we evaluated. Like, this is also very important. So this is so far we have been talking about the AI based dyes. Then I want to come up with like a push-pull mechanisms, again donor acceptor systems. Okay, where you see here this compound is very similar to the previous structure, but the only difference here is like instead of carbon we have placed nitrogen atoms, which acts as a push, which means they're very good donors, and also linker has a very good acceptors. So charge polarizability on this framework going to be enhanced. And when we are trying to make the material, and we started using two different structures, either both as well as zinc and cadmium. The one, the structures, like if you look into the basic structure, there's a herringbone structures. I hope some of you or most of you might be aware of herringbone structures. More or less, the structures are very similar, and the density of molecules and their arrangement more or less very similar, but not exactly same, but more or less similar. But only difference is going to be their dimensionality and topology. Topology means how they are really closely arranged, and what kind of arrangement. Like a J, I hope you are aware of like a J aggregate, H aggregates, and such kind of arrangement. If you come to like in case of like cadmium, the J aggregation is much better aligned compared to the zinc. That's the only difference we observed. Then we try to measure the values and started observing the absorption cross sections, where you see here absorption cross sections values are like these not an absorption cross section. Does this compound show any 2-photon absorption cross section or not? We try to plot it by using fluorescence as well as fluorescence intensity, and we see intensity of fluorescence is quadratically related to the intensity of excitation of the laser. So which shows that this is a 2-photon excitation actually. Okay, and as I said, like the J aggregation of the cadmium is much better than the zinc. Thus, and that of course that is because of the specific topology. Thus, you can see like the absorption cross section of the cadmium framework is much better than, almost 9 times higher than the zinc. So now we are trying to establish the structure property relations, where how to control the packing, how to arrange the molecules in the 3-dimensional framework, and during this methodologies, how we can enhance the optical NLO activity of the materials. And we have evaluated few factors, and we are still establishing it. And the last one, not last one. How much time I have? 15 more minutes. Yeah, sure. So okay, then we have. Then I was we have started working little more into this, a little bit in the application point of view. So if you want to calculate the pressures, and optical activities, then we started using the fluorochromic. How does it play out? So for example, you have a framework. When you apply the pressure, the framework gets contracted 5 minutes. Okay, contracted, and the optical activity gonna be changed. Why? Because once you contract, the energy levels gonna be changed. Because of this, the emission energy is gonna be different. For this purpose, we have used different organic linkers, and almost all are zirconium clusters, but like different organic linkers, and which are again all are piezophoric. Which means like if you apply the pressure, the activity, the strain in the framework is going to be link is going to be changed, and then your band's going to be changed and the activity is going to be reduced. And we want to correlate these values and see here, these are the typical frameworks, and almost all shows the pristine framework is very bluish. But upon pressing or applying the pressures, you see here the band gap got reduced. So you start to see in the fluorescence of green. So the band gap reduced. Then we started observing the absorption cross sections, specifically these two frameworks. Why? Because these values, upon pressing, applying the pressures, the C-axis of this unit cells is significantly reduced in case of LiFM 114. Of course, they both have the same organic linker as well as the metal node, but the only difference is going to be their packing arrangement. Because of the packing arrangement, upon applying the pressures, the unit cell volume is going to be reduced, so that molecules are causing there's a significant change in the significant enhancement or decrement in the strain structures. And during this material, you see here, in case of LiFM, the values in case of high pressure, where the molecules are more strained, has 10 times higher value than the low pressure values, which is resultant in 2000 Gepard-Mayer values. But when you come to the PCN structure, which is going to be here, there is no much in the C-axis. I mean, like it cannot be pressed much. In such cases, you can see very little change in the absorption cross sections, only 2 times. So now you can see here, by using these materials, you can also calculate what is the pressure you applied. Now, once you standardize these values, you can use this one as a pressure sensors, because we use almost like 150 tons of pressure on the frameworks. Okay. And we also did some more work with like a die coordinate and systems and so on. So I don't want to go into more details. Since we have limited time, I want to bring a couple of applications. Of course, I already explained about the piezophoric mechanisms, and the next one is going to be like lasing and pattern writing. These are the 2 specific examples I want to take it up as an application. Of course, we have a lot of other applications like optical limiting, where conversion has a laser damage, but the focus is little less. But I don't want to go into the what is the lasing and so on. But I just want to give you a little of examples where you see here. We have prepared, not myself, like it's like one of our friends prepared a framework, anionic framework, where you have the guest molecules, which are cations, which can be replaced with the dye molecules by soaking the material. You see here, with a different time, the dye molecules are going from the channels and forms a structure. And upon excitation, this compound shows very strong lasing. And this kind of lasing again is at multiphoton, because this is like we are excited with like around like 1064 nanometers, and then you start seeing the lasing actually. And this lasing again, I'm pretty confident most of you are aware, like based on the cavity size, the signals and their suppression influences. You see here there's a decrease in the, when you're using the smaller crystals like 85 to 50 to 30 micrometers, your lasing peaks going to be reduced as well as their suppression going to be increased. So this is how we started using these materials, our two-photon absorption based materials for lasing. In addition, we also use not only 2-photon, and we also use 3-photon absorption phenomena by using the same dye in the different frame. But we could observe the very similar stimulated emission as lasing from the framework. Then this is well and good. Now you have a framework, you have the guest molecules in the framework, and this helps in the observation of like nonlinear activities such as like a 2-photon absorption or 3-photon absorption, so on and so on. But our frameworks are known for porosity, right? Then how can we use the porosity, and how this tunability can be changed? For this purpose, we have used, like our friends have used different solvents. Okay, by using different solvents, lasing wavelengths can be changed. So you see here, when there is no solvent, your lasers are produced around like 650 nanometers. As it increases as you are incorporating different solvents such as like water, ethanol, acetone, DMF, toluene, the laser wavelength going to be reduced into the higher energies or lower wavelengths. And this is because of the energy profile diagrams. In case of polar solvents, how the ICT, which is going to intermolecular charge transfer, is located in case of polar environment versus non-polar environment. So this is how we can tune the lasing behavior, and we can tune it by using different solvents. It means you don't put the solvent there, you put the atmosphere, then the ambience will be analyzed, then the wavelength can be tuned in the lasers, which is very difficult if you take it to the pure oxide systems. But by using metal organic frameworks, you can do it very simple. Okay. Then next one, if you want to get the laser with two wavelengths, can we do it? Yes, we can do it. Instead, in case of that, we use two different dye molecules in the framework, again loaded. Then you start seeing it like the lasing from the one molecule and the laser from other molecule can be observed in the same time. And you see here, in case of like one molecule here, the laser observed in around 600 nanometers. In case of other molecule, another dye molecule, which is LDS 750, your laser can be observed here. But if your framework has both the dye molecules, then you produce the laser with both the wavelengths can be observed. So you see here, our frameworks not only give you like a tunability, you can also enhance the range like a continuum or like a wavelengths produced in the framework easily. So you can produce more wavelengths. Here we use only 2. If you go with the 3 and 4, you can always increase you can always continue. You may get one time the white continuum, white light continuum could be observed. So I don't want to go more into the details, but like I want to come to like we have produced some other mechanism to produce it. Meanwhile, we also use patterning. What do I mean by patterning? So we have the framework. We soak in the silver solutions. Then when you excite with these lasers, the advantage with the 2-photon absorption is like in the 3-dimensional framework, in 3-dimensional like space, you can activate a very specific location, like 0, 0, 0, 0, 1. Like if you take like one position in the 3-dimensional space, you can easily locate it. So you soak these materials in a silver, where reducing activity can be maintained, and during this place, silver can be converted into the silver in the silver solution. If silver can be converted into silver metal, and this can be patterned in the crystal itself. So you see here, you have a crystal, and in the specific location of this one, you can easily reduce the silver and you can pattern it. And this can be used as a data storage or data storage materials. And this is not only done by the silver, we can also do organic reactions, which we use such kind of linker where you have the nitrogen-based, pyridyl-based substituents. Upon excitation with a specific wavelength, it can be oxidized to such kind of structures, which has a different fluorescence. And it's in the crystal. You can see here at a different. You can see here this is a crystal at a different lengths. You can fabricate specific names. So these are the basic reports so far how this multi-photon absorption has been used, and since the area is very new, it's a long way to go and to establish the various optical activities specifically into the applications. We have done enough of structured applications, we believe. So now we are totally working on those applications like lasers and patterning and so on and so on. With this, I would like to thank Department of Physics of IIT Bhilai and AICTE for giving me the opportunity to present our work. And I also would like to thank you all of you for your kind attention.